Hey Jeff,
Hi, Miss Betty. How you doing?
I'm good. I was trying to paste in what I pasted to um, Mike, but would you like me to start you off? I would do two things. I would say just to want to remind everybody that you want to put your questions in the Q&A forum, and if you really like a question, thumbs up on it for other people's questions, and so that those rise to the top. And then take it away, Jeff. Is that a ponytail I see?
This is the COVID haircut, right?
Oh my word!
I have not had a haircut since basically the beginning of the year, late 2019.
Oh my God!
Other than the front,
Right.
and occasionally the scraggly beard. But This was bothering me so bad. It was hanging down around the lower neck area. And I was doing a test yesterday with the camera. And I'm thinking, I'll throw it in a ponytail. So this is the first time I've ever had a ponytail, and I had to do it myself. And it's already fallen out twice. And it's like, oh, you got to wrap the rubber band really, really tight. I'm kind of keeping up on the things I've seen in my life.
Oh my God!
With women doing it, girls and women doing it, right? It's like I should have asked Cindy about the real things. But anyway, so I've been wearing a ponytail. I'm on second shift now. I'm already finished one class for today. An EMBA class that we got done 2 hours and change ago. And so now this is second shift. There you are.
I forgot. I'm like, I don't even have my camera on. There you go. Because that would be my phone. And
you might see, I don't know if you let people in or not, I've got a Jeff Carroll monitor that is I use a secondary screen so that I don't have to ask people, can you see? Am I sharing?
Exactly. I do that.
That makes more sense. So, I see Sherry just said, once I can spell Sherry's name.
Typing. So hard.
Okay, so I just sent it up to Sherry. She said, let me know when you want me to land. See if she's going to let me watch her in. I don't know has what and does what, but that's okay. I know we'll get there. And I was trying to detach chat and participants, but it doesn't work. When I was practicing on my own, I could, but that's okay.
Well, it might be because that was the meeting, and this is that might be.
Yeah, I see what you're saying.
And some of the buttons are missing.
Yeah.
So I
Can't
don't-
let anyone else in until I let everyone know.
No one is
Let me know when we're good to go, and I'll let attendees in. Well, what else do we need to do here? So, is it time for me to do sharing yet, or do I have those credentials or that capability? I don't think I do.
Yeah,
Nope.
go and try to share just to make sure.
Oh, there it is. All right, I am going to share that screen there.
Oh, that looks good.
And it's really annoying that I don't get to see that sharing, do I?
Okay, so here's the deal. What you might want to think about the fact that you have to the left the library of, I don't know if those are files or those are VMs but it says Win7 on the top, Wireshark only VM real workspace, so I guess they're VMs.
Yep.
Just kind of slide it over a bit and give yourself some more space.
Well, the thing is, I need to go access them as I go through.
Yeah, but you still got a lot of space to the left. You can slide it. Look at me pointing at my screen. Like you can see me point at
Yeah, I can see you pointing it. I'm just.
But in the lower left-hand corner, you can slide it a bit to the right so that you're flush more to the left. So take your eyes all the way down to the lower left-hand corner, just above where it says, that slider. Now bring that over to the Cooking with gas. like fluff and puff or anything, but I do put on some lip gloss. Okay.
That out of the way so I don't trigger that. So, and these screens are going to all dynamically change anyway as I fire up different VMs, but that's okay.
I like the stuff you have on the side with the weather and the times for. That's
those,
nice.
Those are Windows 7 gadgets. You can't even get that anymore. You have to download a gadget application that still works with Windows 10.
Right.
But I mean, it's like this week I've had people in various EMEA, South Africa, Abu Dhabi, and so I can kind of go, I know where people are more or less
right.
and I can address them accordingly.
Exactly.
And it comes in.
I'm
so slideshow going.
See, if I could use my camera, I would take a
Well, I've got 3 monitors here. So one side has got discard. Well, actually, this laptop can do 4 monitors. And in fact, in practicing, I thought about putting something up, a smaller screen, up above my main, and that way, instead of looking slightly down, I could look more dead on to the camera. And because I've got a script file that I'm going to be running with down here. So I'm going to be up and down a lot when I go to the demo. But anyway, it's all good. We're not charging people thousands of dollars to come and listen, so, but it doesn't mean they're going to get jumped, so.
Exactly. Professional side.
Yeah, I want to look nice. And,
you do. This looks awesome.
Okay, are people asking questions in Discord, or are they mostly asking in
So
chat?
here's the deal. I will tell them that they can only ask questions during the session in the Q&A. Discord is for after the session. Because I can only look at so many things at one time, and so I'm just
right. Okay. All right, so I'm going to keep chat open, kind of, but the Q&A more open.
Now remember, I'll watch the Q&A and let you know if there's anything on the Q&A or the chat. Other than that, I will not do it unless I push you over.
So I've got 1 to 2 or 11 to 12 plus 15 minutes. And then actually lunch breaks in there so I can see it before, except somebody will probably shut us down. So.
Yeah. So after an hour.
After an hour.
You're ready to start Q&A. But, I will gently nudge you towards Q&A.
Well, and also, I mean, let's do leave it. People can ask questions. Maybe they won't answer immediately, but I'll kind of look at that as well. There might be something that would be more pointed to answer than an hour away, and then it's kind of like, well, what was that even related to?
Yeah, because it's kind of frustrating. There's no way for us to get aware of, figure out and, so you copy and paste your questions. Also, they take advantage of yours.
Okay. I think we're basically ready. It looks like Sherry's wanting to open it.
Yep.
All right. Okay. So I just sent her that note, ready to open. Didn't spell well, but gotcha. She's going to let people in. All right. So hopefully I'll start to see my list as well. There's the participants I also wanted to see. And I was kind of nervous initially about all this because it's traditional face-to-face SharkFest. You're up against 2, 3, 4, 5 other sessions of generally better things that I'm talking about, and I can't go, but competing, and now it's basically competing with one other session. Well, that's ought to be kind of fun.
Now I got a chance.
Really?
I once went against Laura. Laura was doing a session, Gerald was doing a session, and Betty was doing a session. I'm like, Janice, you're killing me.
It's kind of like, can't you just let them go solo, please?
Well, I just told everybody to go to one of their sessions and they could record mine.
All right.
Don't waste your lifetime on me.
watching computer, it's all muted. It looks like we're already recording.
It'll take a lot of time to make it right. Will you still be here when I'm fine? The answer will tell me what I know. Oh, comfort me. Oh, comfort me. Then I'll go. Oh, comfort me. 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 I will follow. Call on me. I will follow. Call on me. I will comfort you. Tell me 'cause my journey is the same. Broken down and broken many things. I know that you can carry the weight of the world with you. Oh, comfort me. Oh, comfort me. Oh, comfort me. Oh, comfort me.
Well, good morning, good afternoon, and good evening to everyone. Just want to let you know that we're about to start for Jeff Dow, and we're going to talk IPv6 and security assessments. But before we get started, I just want to welcome everybody to SharkFest in case you haven't been already. And to remind you that while you watch the meeting, if you have questions on anything, please go ahead and put them into the Q&A versus the chat. And also, too, if there's a question that's on the Q&A that you're like, oh my gosh, that's a really good one, go ahead and give it a thumbs up, and they help rise to the top. And that way, when the hour's over and we're about to go ahead and do Jeff's about to do answers, he'll know which ones to focus on. So take it away, Jeff.
Thanks very much, Betty. Welcome everybody to our SharkFest virtual, and we're going to have a great time. So as mentioned, I want to talk a little bit about IPv6, and I have to give it the nice, pretty words of the security assessment tools. That's for the layers 8, 9, and 10 view. You know, if they see the words hacking, sometimes they might not be happy about that. But you know what? That's kind of what I'm talking about. How IPv6 as I'm not going to call it anymore a new protocol, but as one of our core infrastructure protocols, can be attacked. And from sometimes very seemingly easy looking modes. And very honestly, it is as easy as it is in an IPv4 world. But I want to go through a little bit about what we get to see from that aspect. So I'm going to do some IPv6 basics. I've got slides. You know, it's a show, it's a presentation. You got to have slides. It's just the rules. But I'm going to go really, really fast. Okay, it's quick review, mainly because there's some key aspects or key components within the protocol that I want to show, and that we're going to see in Wireshark. It is a Wireshark conference, right? I'm doing lots and lots of stuff in Wireshark, and with a focus on IPv6. I'll talk a little bit about V6 in Wireshark, kind of the way I do it. You know, Jeff's V6 in Wireshark way. I want to talk just a little bit about the security air quote vulnerability in IPv6, and then we're going to do some attacks and see what that looks like. So as that, let's talk about an IPv6 address. If you've never played with IPv6, you're behind the time. All right, it's 128-bit colon hexadecimal, and you could see colon and double colon in an IPv6 address, depending on, I'll call it some X components, some X variables. Let me get a little laser pointer. As you see down here, the 128-bit address is divided into 8 16-bit groups separated by the colon, as we mentioned earlier, and each one of these groups, 16-bit groups, is generally known as a hextet. It could be a quibble. The more mathematically correct term would be a hexadectet, and that's just kind of hard to say. So hextet is the generally accepted rule. It's alphanumeric. So look, you can put words in your V6 addressing structure. We've got 6lab, we've got foosball, we've got Dallas. That is great. Don't do it in production, okay? Don't do hex words in a production network because you have narrowed the attack vector considerably, because it's really easy now for those that are wanting to do any kind of recon to pull down the hex 4-letter databases and feed that in. And again, really made their lives easy. Do it for lab, do it for fun, but don't do it on any network that has external possibilities. The 120-bit address, most people go, oh my goodness, that's going to be so much more to remember. How in the world am I going to be able to remember that compared to a 32-bit address? Actually, it's not near as hard as a lot of people think, mainly because the first 64 bits are your network and the last 64 bits are the interface ID, or what we might also call a node ID. And then we basically have our CIDR notation to give us the prefix length of the network. Now, the common thing is a default network size in IPv6 world is a /64. A /64 would be, I would say, kind of similar to an IPv4 subnet where a lot of us will do a /24 for a VLAN or for a particular subnet space. Just general purpose user type networks, let's say. The /64 is the way we do it in v6. And in fact, some operating systems, you can't even change that behavior to say, I don't need a number that big, because a /64 means I can have a network segment, a layer 2 domains address space that yields 18 billion IDs, all right? A lot of people look at that right off the bat and say, that's wasting addresses. Well, it's not. Don't worry about it. Accept it, because you don't get a lot of choices. But I would say the attackers, all right, once they find out the network prefix, and that's not that hard to do, they only have to deal with the last 64 bits. And again, if you start putting in hex words in your addresses, you've just made it so easy. Now, when I say things like that, if you ever see Facebook's v6 address, their 5th and 6th hextets are Facebook, FACE::B00C. So they didn't listen to Jeff, but you know what? They're Facebook. They don't have to. So little things like that. In an address, we do have some shortcut capabilities or shorthand notation. We can condense down a single or up to multiple contiguous groups of zeros, hextets of zeros, to a double colon. All right, so we see two variations of this middle address where the second and third hextet were condensed to a double colon. You can also drop leading zeros of any hextet. What you can't do, though, and I'm going to go to the next slide, is you can't do two sets of double colons because we don't know how many bits are represented between those. So that's why in this particular example, option 1, we concatenated down the shorthand notation of the second and third hextets, did leading zero dropping, or option 2, we did the 5th, 6th, and 7th hextets down to the double colon. The basic rule of thumb is whatever yields the shortest variation of this address representation is the considered best choice. So all three of these would be a accurate and working example of a v6 address. Not all operating systems will use the shorthand notation. Some you may enter it in longhand and it will concatenate it down in shorthand. Some you may put it in shorthand and it'll expand it back out. Don't worry about it, just kind of understand the ruling. The only other bit is are your alpha characters upper or lowercase? The RFC says put them in lowercase, but different operating systems do it differently. We don't care, okay? And I don't mean that disrespectful or to be short. It's just, it doesn't really matter as long as we've got an address that works. One of the key things about the various address types in a V6 world is there is no broadcast traffic, all right? We've got broadcast in V4, we use broadcast, we look at broadcast all the time. And in V6, we don't have, quote, broadcast defined traffic. It's considered an on-link multicast. So we have a specific multicast prefix for on-link and then a different multicast prefix for off-link. And so one of those little tidbits of differences that we start learning. In the address scopes, we have similar type of definitions, i.e. there are link local. We really see that naming convention in a V6 world. In the V4 world, we knew that as that a PIP address, a temporary address when there is no static or no DHCP service available on a V4 segment. We've got that 169.254/16 address. But remember, it goes away as soon as you get a static or dynamically defined V4 address. In the V6 world, your link local address never goes away. And in fact, it is used for on-link communications. All right. So you will always see your link local. You may then also have a routable address. Typically, we call that the global unicast, and it's routable both internal and external. It's routable to the internet. In the V4 world, we kind of call those the public addresses. We also have a private looking address called the unique local. Has a specific prefix for its definition. And it's similar to RFC 1918 type definitions. It's not naturally those same, but it's a similar in concept. In some of the address types, I really want you to focus kind of on these two center ones I have highlighted. Link local V6 addresses have a prefix of FE80::. All right, first 64 bits, FE80. That is reserved, and it is not a routable address off link. All right. You could have multiple interfaces in a device, whether it's a router or a desktop or a server or whatever, and each one of those interfaces could have the same link local address. Quite often they will, and that's because they're not routable off link. All right, so we will see some of these FE80 prefixed addresses. The other address that we're going to focus in is these global unicast. The global unicast addresses, as assigned by IANA at this point in time, are from the 2000::3. So basically, 2000 through 3FFF are valid, routable to the internet, capable addresses. Whether or not they are done that way, that's another story, all right? But it's a possibility that it can be. So we're going to look for these two types of addresses in my lab scenario here. The multicast prefix addresses, all right? We're going to see some of these as we go through in our lab environment. And this is not the complete list, but these are the most common ones that we see. So kind of be on the lookout for some of these FF02 prefixed addresses in the traces as we go through these. How do we get that interface ID? Part of the design concept of IPv6 was they wanted it to be self-working. In the days that this was thought about, this is the early 90s when they were saying that we're not going to run out of these IPv4 addresses. This is before the public internet days, very shortly before the public internet days. And the concept was they figure they're going to run out of these 4.3 billion addresses because everything was considered a public routable address. It had to be assigned. And it was all manually done. We didn't have DHCP at that time. So everything had to be done. So their idea was, one, we need another protocol that's going to be more extensible, and two, we'd like it to be automatic. So their idea was, one, we need the interfaces to self-generate their own interface ID, their 64-bit portion of the address. We will then actually use the router on that segment to generate what we call a router advertisement and provide these client OSs the network prefix. And the thinking is now the router gives me my prefix, I generate my own interface ID, and ta-da, I have a 128-bit address. So they came up with the idea, well, let's use the MAC address. The MAC address is unique on a network interface, but it's only 48-bit. But they were able to take an existing IEEE standard known as the UE64, and they say, fine, that took a 48-bit number and made it into a 64-bit number by adding in some padding in the middle, FFFE. They further said, but that's a UE64 number or value that we're going to use for a number, and they decided that they would take an unused bit and invert it, and it's the 7th bit of the first byte. Invert that, and then now I've got a unique 64-bit number used for IPv6 addressing. And this was all great and wonderful, except there's a few flaws here, right? All I need to do is look in the middle of this 64-bit interface ID for FFFE. Then all I need to do is go reverse out the first 3 bytes, find out the manufacturer, go to the manufacturer website. I can figure out probably what kind of device it is. If I've got a bunch of addresses with the same device, I know what kind of network I'm on, or at least what's on that network. So everybody said, this is not secure because I'm traceable. My interface ID will always be the same. So another variation was defined to be able to create an ID, interface ID, using a random number generator. Initially, when this came out about 10 years ago, some of the manufacturers were using it. Some of them were still using the UE64. Pretty much this is the way all the vendors at the client and most server OSs operate. So now we've got a random 64-bit address, and they further added to it and say, let's do another one, a second one, and we'll call that the temporary address. And we'll further say we want that temporary address to change on a periodic basis. And the temporary address is going to be the most primary address that I'm using for my communications. And because it's going to change periodically, I'm not traceable. All right, I can't be followed. They don't know that Jeff's here, Jeff's at Starbucks, Jeff's at home, Jeff's traveling or whatever, because nothing to tie to Jeff. Well, yeah, this kind of works. How you get to this random number is interesting though, because one particular entity of an operating system vendor up in the northeast of the US, we'll leave it at that. Guess what they used as their start point for their random number generator? The MAC address. They took the MAC, they ran it through some hashing algorithms, and ta-da, they came up with an address. So they've slowed us down 15 seconds. But nonetheless, this is still what goes on. Now, the not so fun news is that because that temporary address can change on a periodic basis, it may change while you're troubleshooting, especially a client server application. And you're rocking along with your trace file flying by, and then all of a sudden it just stops. But nobody's yelling that the application quit. It's still going, and that's because your address just changed. And because of the design portion of V6, and we'll talk about a piece of that here in just a minute, you can change addresses on the fly, and it's okay. All right, but it's not good for troubleshooting. So a lot of people will actually turn that piece of functionality off just so that the addresses will stay randomly static, which is probably the 2 words that should not be used together, but that's about the way it works. How these things can happen, how I can change addresses in the middle of operating and nothing break, is because I have actually 2 types of lifetime timers now on an address. I have a preferred basic working lifetime value, and then after that has expired, I have a little bit more time called a valid to basically allow me to finish communications with this address while I start up a new address. And so I can actually readdress a V6 network on the fly, middle of the day, middle of production, and nothing would break. We can't do that in the V4 world. I'm not going to say we should do that in a V6 world, but these timers help V6 in its operation in a good mode, but they could also cause other grief in a not so good mode. A little bit about the neighbor discovery protocols. In the V4 world, it's comprised of about 3 different RFCs. In the V6 world, it's all under one RFC to do similar types of requests. We are going to focus basically on these first 5: neighbor solicitations and advertisements, router solicitation advertisements, and the DAD test, the duplicate address detection. Basically, I always have to validate whether my address is going to be good or not. Part of what this means is we can't summarily go block these ICMPv6 protocols or globally block ICMPv6 on network segments. We need some of these ICMPv6 components to operate just for V6 to operate. So a little bit of difference in perhaps that operation. So again, these are the main four that we're going to look at: router solicitation advertisement, neighbor solicitation advertisements, and you can see these IPv6 type numbers. This is that particular mode, router solicitations. Basically, when I come on link as an interface, I'm going to send out a router solicitation basically saying, is there any V6 routers out here? And if I get an answer, great. If I don't get an answer, equally, okay, fine. It just means I'm not going to be potentially able to talk off net. What I should expect back from a router solicitation message is a router advertisement. It's going to tell me all kinds of things. One, I'm a V6 router for you. Two, it's going to have some flag settings that tell me as a client how I'm going to deal with my addressing. I'm either going to accept the router prefix or the network prefix and add my interface ID to it. We call this SLAC, stateless address auto configuration. Or the router advertisement is going to say, tell you what, go ask for a DHCPv6 server to get an address. And so then I will send out a DHCP solicit message trying to find a DHCP server. And this again was all part of the automated process or automatic process of IPv6 addressing in a world. So router advertisements are absolutely key, crucial on this network. They occur periodically as well as in an immediate reply to a router solicitation message. Neighbor solicitations, basically what we think of is I want to find out is somebody there or still there. I use the neighbor solicitation for my duplicate address detection or to find out if a neighbor is still available or effectively not available. The DAD test, I must run a DAD test for every V6 address. Link local, GUA, EULA, doesn't matter. Anytime I want a new address, I've got to run a DAD test to validate. Initially, the DAD test used to be run before you could start using that address. The problem was sometimes it would take longer than, say, valid timing to get logged into things. So they're they redefine the RFC to say, we're going to do deterministic DAD. Go ahead and get an address, run the DAD test, but you can start using it unless the DAD test fails. So it can actually create additional problems from a attack vector viewpoint. Neighbor advertisements, basically what it sounds like. I'm looking for a particular neighbor, whether I'm trying to do a ping, and we would think of it from a V4 world, do an ARP for that. Now we do a neighbor solicitation message. Those different options, flag options that are available in these router advertisements, this is basically a chart. There's primarily 4 flags that we're looking at from that client perspective to help me determine how I'm going to derive my V6 address. And so these become a little bit even more important. Just a quick look at the DHCPv6 process. It's very similar to, quote, the DORA acronym process. Now it's called a SAR. I would send out a solicit message if I am told to. I'm waiting for an advertise from a DHCPv6 server or servers to say, yeah, here we are. I make a request for an address. They give me a reply message. So we're looking for this SAR functionality as opposed to DORA. Looking at V6 in Wireshark, all right, however you might use Wireshark, if you use coloring rules and you use columns and how you do your layouts, totally okay. I'm going to be showing you kind of my V6 world where I've got very specific colors for very specific V6 protocols. Whether it's a live trace or a static trace, I want to know things occur, like router advertisements, like router solicitations. I've actually retweaked my DHCPv6 color to be different than just traditional ICMPv6. However you, of course, want to use it, fine and great. The nice thing about it is we also have 3 primary display filter definitions. I PV6, ICMPv6, and DHCPv6. And then you can go down and have multiple other subcomponents underneath them, just like we do all of our other display filters. You can almost see I put a bunch of display filter configs up in my display filter bar. I've even got multiple profiles for different V6 views, as well as many, many others. So yeah, a little bit about display filters, where you get them. Again, the 3 primaries plus all the ones below that. Life is good. Just a little bit about my config profiles. So however you might use Wireshark, that's all up to you, as they say. One of the great things in your V6 learning journey is that you should probably play with this in the lab. You should play with it from a basic learning aspect, and humbly, you should play with it from a proof of concept of bringing V6 into a real production environment. Get these traces, make some comments in the packet annotation capability so that you can see things like, this was a good router advertisement, or something occurred here, or something didn't occur here, whatever that is, but so that you can be able to go follow up on this. It's new, it's different, lots of different parts and pieces going on here in a V6 world, as you're going to see. So make these comments in your lab files. So what are some of the security concerns? If you haven't already picked up on them, and it looks like we've already got a couple of comments going on out here already. I just kind of seeing some quick highlights. All right. If we're using those UE64 addresses, it's so quick to figure out based on if it's got a valid IANA defined vendor prefix. All right. Now, if you're just making up your own MAC addresses, that makes it a little bit better, but still, it's a really easy thing. V6 is an enabled protocol in most operating systems, has been for about 8 years now. And if you think going into Windows and just ticking the box off or unticking the box, saying you've turned off the V6 protocol, you really haven't. But wait, you looked up that 6-year-old IPv6 bulletin on how to go into the registry and turn off V6. Well, it really didn't. And they rescinded that and say don't do that anymore because they require V6. So just because you may say, air quotes, you're not using IPv6 in your production network does not mean it's not running. Or even more fun, it doesn't mean it can't be lit up. And I have another presentation I do on an attack of a real network from the outside world to the inside. I get in, I light up a V6 router, all these nodes get V6 addresses, and I start recon on the V6 network. And who is watching me? Well, nobody. They're not running V6 in the production network, so of course they're not running any kind of intrusion detection environment in V6. So here I go jumping around the network on V6. We'll leave that one the way it is. There are not many, there's quite a few tools that support this V6 testing and assessment, security assessment capability, right? And you can hack with them. You can have rogue router advertisements. There's already been some comments in here about that. So we have first hop security mitigation capability in most enterprise class or at least good managed infrastructure devices. We can prefer router advertisements to be on the trusted uplinks, et cetera, all right? But still on the inside of the network, as long as we're not running, managed infrastructure, then yes, things can be attacked. We'll leave it at that. Temporary address gets more in the way for potentially troubleshooting, but it still should change. The difference is different OS vendors use different algorithms on that temporary timing. So that sometimes ends up to be a little bit of a challenge. You can't just block ICMPv6. Some people try and then V6 just doesn't work. We've got different multicast addresses that can be used. We've got all kinds of things here in spoofing between RAs and DHCP V6 operations. Literally everything again in V4 we have in V6 plus a couple of more. All right, and there's all kinds of noise out there about how it's so insecure. Well, it's only insecure because somebody humbly may not know enough about it, may not get into the details. And so that's why I pretty much say definitely should be learning V6. I give this presentation and my attack presentation to InfoSec groups, and they go crazy. The red team eyeballs light up because they go, look at this new attack vector, and blue team eyeballs light up and they go, wait a minute, We're not watching V6 because we're not running V6. Yeah, well, you better start watching V6 because it's now the new attack vector and it's great. Okay, from a red team perspective. I talked about, their addressing. Don't use hex words. Well, there's also some other easy things that people are doing. Basically, this last bullet, the world is going, great, I've got to learn another protocol. You know what? I know my V6 environment. I know my my V4 environment. I know my V4 addressing. I'll just insert my V4 address into those last 4 hectets. I'll do things like 10:1:1:1, or I'll convert it to hex. I'll be cute and convert it to hex. Well, guess what? The first thing I'm going to do to attack a V6 network is I'm going to start from 0 and go to 254. Okay, I can search that big of an address very quickly. I'm not going to search an 18 billion possible network address block in literally like 40, 50 years, at least with a single heavy duty computer. All right, it's not going to happen. We don't need to though. Right now, people are taking this very easy. They're trying to take the easy way out, and it's humbly, in my opinion, to their detriment. Don't do it. Here's the time to beef up your security, because this is what I'm going to do if I'm attacking. If I'm red teaming this, these are some of the key things I'm going to do, because I can pop these out in seconds, and everything else is going to take a lot more time. Other types of attacks: neighbor discovery, DAD test, RA, DHCP V6 spoofing. I'm going to show you a few examples of these as we go through. Here's a basic look of this lab environment that I'm going to show you. It's all running in virtual machines. We're going to spin this up slowly and let you see some of the operations, but this gives you an idea of what you could see. This gives you an idea of how you can learn about this protocol. You don't need a lot of fancy things. Everything here is almost done for free, even to the point of even Windows clients using Microsoft's anywhere from 30 to 90 to 180 day free trials. Do not run these things on a network without written proper authorization. You may have remembered that bit that occurred about 2 years ago now, or a couple of guys were doing some recon on a network and quote got caught, got arrested, and they thought they had a get out of jail free card. Well, it didn't last them out of jail for a while. It took a little bit. So don't be running these things on a network without permission. And just because you may have the keys to the kingdom does not necessarily mean you would have permission. Just saying. With that said, here are some of these tools that are available. Publicly available. In fact, the THC IPv6 and the SI6 networks V6 toolkit, both of these guys wrote these for themselves to learn the protocol, to test the protocol, and then they put it out to the open source world. In fact, these tools are embedded in Kali Linux now, and actually have been for a number of years. Nmap has updated. I'm going to run one Nmap scan, all right, to run on V6. Basically put a -6 on an Nmap command, and ta-da, it's going to go do a V6 operation. Now you've got to have V6 addresses accordingly, but nonetheless. You can also do, I love it, packet forgery, all right? You can do a little bit of that with the SI6 kit, but these other packet forgery programs, and these may not be the exclusive list, but they definitely do support, trying to create some specific V6 packet. And in all cases, you're using this as learning and troubleshooting an environment to validate its operation. And we're going to nod, yes, Jeff, that's how we're going to use these tools. All right. Quick little cheat sheet I put together. There's probably about a dozen different V6 cheat sheets out there. Feel free to go grab that, take a screenshot, and have fun. The last little bit, I'm gonna just pop you through. There's a number of different books that cover V6 from different aspects. All right. And I'm just going to kind of pop through these real quick. Different Wireshark related books, a number of books on planning, on V6 in Windows, V6 in a Cisco world, V6 generically, and V6 in a Microsoft world. Some of these books now are approaching 5-6 years old, and we actually had about 3 iterations of books: the early 2000s, the mid 2000s, and the mid 2010s. Is about the date timing of our books. And there you have it. with that said, I've been flying really, really fast. It's time for a demo. So I've got my little network over here. The first thing I've got running is a VM out here that is sitting on this network so that I can find things. All right, a couple things I want to show you real quick is that I'm running on this computer an interface in that network. It happens to be VMnet 9, okay? And I want you to see these things because this is, in my opinion, really important. All right, this VMnet 9 does not have a GUA address. It does have a link local. It has a v4. I don't care about that truly because I'm not really going to do any v4 work. So we see that we've got Wireshark running on this network and no other applications. So I'm going to fire up my server, Windows 2012 server. It's going to provide me DHCP v6 services, DNS services, and web services all on a dual protocol mode of v4 and v6. Again, I'm really only wanting to deal with v6 right now. So we've got to kind of let that go. But while that's going, look at it. We've already seen some traffic occur. I haven't done anything other than turn on a machine. But already we see things like router solicitations, all right? Happens to be coming from this machine, C7F9. I'm going to kind of focus on typically the last 2 bytes of a MAC address. When this machine comes up well enough, we'll go look at it and see. As a for instance, my machine here, I'll show you the VMnet 9 MAC address 0009. Okay, and if I come over here and look, we should start to see some things going on in this trace file. Right now, we're seeing a bunch of these 1490 or 1994 addresses. But eventually, I'll start to see some operations from that other client, or from effectively my client. So we're seeing something. The DAD test is when the source address is a : double colon. It's all zeros. All right. So the double colon. I'm going to make a quick comment in here. All right. You'll never have more than a single double colon, and no matter how many bits you're concatenating or compressing down to zeros, it's always a double colon. This is all zeros, okay, going out there. And then they're sending out a multicast message and they're looking for, does anybody have this address? If not, I'm going to use it. And there's that, a global unicast. Look at that, 2001, all right? And look at this FE80. And if we look at the MAC address, Charlie 7 Fox 9 is for both of these. So that's the same machine. And if I come over here to my server and look at it real quick, we'll probably see, if I can spell, there we are, 2000. And he's got a linked local address of Delta 2 Echo 9. So let's go over here and see what he was wanting. Oh, I didn't go further enough down. Delta 2 Echo 9 was too far up. 1994, last hextet. So this was just the server coming online. Now, in a Microsoft world, they have the interface for v6 configuration very similar to the v4 world, meaning that for v6, you have either a static address option or a DHCP v6 option. Now, this humbly, I don't think is the right way. I think it should be wait for the router advertisement before you do that. But they didn't ask me, and that's okay. So what's actually going to happen in a Microsoft world is that the clients are going to do a DHCP v6 if that box is ticked. So eventually, I should see from my client that operation. Now, I can also affect that by disabling my interface and re-enabling, basically restart it. And if you saw a little bit of Wireshark going on back here, we should start to see a little bit of traffic flying around. All right. And we can start to see there was a router solicitation message that came through. Here's the DAD test, and should see another DAD test right here. Okay, DAD test for Echo Echo for Charlie, which should now be this guy. Oh, I went too far. VMnet 9, Echo Echo 4 Charlie, and look at that. Now he's got a v6 address because he came on link. He's checked for DHCP v6, so he just did it. We don't have a router yet, but he did it. And I could come over here and look at DHCP v6s, and I could effectively see he came on and said, hello, any v6 DHCP servers out there? And my Microsoft Windows server said, yeah, here I am. And basically said, oh, okay, fine. Can I have an address? Yeah, sure. And here you go. And it replied back, and we go way down in here and look at it, and we'll eventually find out that sure, you can have 2001 DB8 lab base 104. And we saw that over here a while ago. He's got 104. So ta-da, we've got a v6 network all up and running. Well, guess what? That server is sitting over there on 2000, but the server code actually also is set for DHCP v6. He does a DHCP v6 basically to himself and gets an address. So he's got two addresses. I would normally go turn those bits off, but we want to see them. All right, so now I've got a real good set of server addresses. So I think I will try to ping it. I've got a client, I've got a server. Let's see if we can ping 2001 DB8 happens to be a 2001 DB8, a reserved prefix for internal networking and exampling, and we'll go to 2000, and yay, ta-da, we're not, wait, why aren't we pinging? Okay, I've got a global unicast address, my server's got a global unicast address, and I'm not pinging, and that's not funny. And actually, that is correct behavior for a v6 world. That is not the same type of behavior in a v4 world. In a v4 world, if two devices have an address and the same network prefix, they can ping each other as long as ping is allowed. In a v6 world, a global unicast address means I've got to have a router, and I have to actually ask my router, am I doing an on-link or an off-link action? If I don't have a router to ask that question, I can't use my global unicast addresses for anything, even though these two devices are on the same layer 2 domain. All right, again, that is not what we normally think of operational world. Well, no, it's just because it's not like v4. However, let's do this just for fun. Let me get my v6 link local address. I want to make sure that my pasting is working. All right. And I'm going to go over here to my computer, and I'm going to ping, and I'm going to ping that address. And I also have to say from which source interface, and I happen to know that VMnet 9 is from source interface 13. So now I'm going to ping my server's link local with my link local, and it works. Ta-da, life is good. All right, life is great. But I didn't have a router, so I'm going to fire up a router next. And this is a little open source router. That's not the router. Where's my router? Oh, there's my router. Sorry. Okay, now we're going to fire up the router. And this will take a few minutes. But what I want to do is jump over here to Wireshark, bring up just the standard v6, and make sure we see some things. I expect all kinds of stuff to happen when that router comes online. I expect it to do some DAD tests for link local and GUA addresses. I expect its router advertisements to be seen by these clients, and perhaps the clients do some things, and we can start to see some traffic already occurring just because that router came alive. And I'm going to back up a little bit. You saw some DAD tests already happening. You see this router advertisement. It came out because the router code came up. If I look in this route advertisement, I can see down in here the network prefix is 2001 DB8 lab base. I can see some particular flags that are set or not set. And in this particular case, what we call the Slack flag, the address flag, is not set, but we do have some flags set for managed address, which tells the client, hey, go ask a DHCP v6 server if it's available to help you out. And so eventually we would start to see additional DHCPv6 query messages starting to come through in this environment. We haven't yet, that's okay. If I fire up another client, let's bring in this little Windows client right quick, we'll see some more traffic. So far, this is the good days, right? We're learning, we're seeing some things, we're happy with the traffic that we've got, as it were. And every time you light something up, a little bit of different action or activity occurs. Look at that. There was a pink packet just came through. That's the router solicitation message from that Windows 7 box. The router replied, and pretty soon thereafter, we should see from this AB72, we should see a solicit message. We'll look at there, AB72, sent a solicit. The router, or excuse me, the server, DHCPv6 server replied. And the client said, could I have an address? The server said, sure, you can have an address. And why don't you take address 103? And so we can go over here to that Windows client and go look at it. And we'll be able to see some things like its address should be 103. And looky there, there it is. Let's back up and look at another thing. Can I ping my server's public or GUA address now? Why, yes, I can, because my client could ask a router, what kind of traffic am I going to be sending, on link or off link traffic? I can ping that other Windows computer because we all know we've got a router to work with now. So this is a good days environment. What happens when you have not so good days? All right, let's see this. I've got a router that I'm going to fire up. Once it comes up, we will see some of the flags that it's got. I'm going to very specifically filter out to V6 router advertisement traffic. Right now, we see all of these RAs are coming from, quote, my good router. All right. Once that other router that comes online, and it may be, quote, misconfigured. All right, air quotes again. And we want to see what happens. One, when that router advertisement comes out, and then two, we might see some other actions occur on our network. We expect those things, and I'm impatient, but I know as soon as I go over there and look at that, the things will start happening. Oh, there's one right there. Finally, 9480. We look at the network prefix and we see it's 2001 DB8 200 bad. Oh no, that's not a good thing. Let's go look at the rest of the V6 traffic going on around here when that occurs. And we should start to see some things occurring when that happened. Bring this down a little bit. And now there's another flurry of activity. There is that router advertisement again, the 200 bad, and varying things did happen. I can't go into all those details, but let me just show you what occurred most likely in this environment. Look here. I used to have that 2001 DB8 lab base 103. I no longer have that. I now have two 2001 DB8 200 bads. All right. This tells me a couple of things. One, I got a rogue router because I know that's not my network prefix. Two, because I have two addresses and one of them called a temporary, I have different flags set in the router advertisement that I acted on here. I have the A flag on, which says router gives me my prefix, I generate my own host IDs. I can see that I still have cached two different gateways, the bad one and the good one. But I see my addresses, right? I'm no longer seen in my normal world. I can look at the addresses to see show adder interface equal 10 and see how long my timers are for. And I can see that the timers for these 200 bad addresses are very short. Now, partly done on purpose. Normally, we would think of timers for these lifetimes to be in the mode of many hours to days, perhaps. But these timers are very short. So what happens is periodically, if those times expire, I'm going to ask for another address. Or If I receive another RA, I may act on that RA right then and there. And that's another part of the thing, is that depending on how the vendors implemented their actions, they either say, as soon as I get an RA with anything, I'm going to do it. Or they may say, no, I'm going to wait for my current addresses to expire and then I'll do it. Or like in this case, this is my Windows 10 machine. I have both my, I'll call it my real network v6 address, and I've got some of these other addresses. So depending on X would depend on where my traffic is going to try to go to. And all of this is because I threw up a router that had a different configuration than my other RAs. So if we look very quickly at my good router, the A flag is off. If I look at the rogue router, the A flag is on. That one bit can do a lot of damage in a network. And we can kind of see some of that going on here. You know, we look at the different traffic. Let's go to DHCP-v6 RAs. This is a handy view. Look at a router advertisement and then see if there's any DHCP-v6 traffic right behind it. And if it is in very close proximity, then typically we would say, well, that router advertisement is different than my normal. Well, I've actually got a profile over here. I think it's on this machine that has the two flags that I'm most concerned with. And we'll look at only router advertisements and we'll look at the flags. And my production world should have M set and A not. But look at this rogue router. It's got M not set and A set. So very quickly I can go, okay, where's that guy coming in, find it in my infrastructure, and one, either go turn off that port, or two, I might implement what's called RA guard if that device supports the RA guard functionality. And it basically, RA guard says trust RAs from only certain ports. So all kinds of very fun stuff that you can do with, in my case, color rules and columns and profiles, the whole bit, and I can bounce around different ways. This has all the 4 flags view. And then I'm going to go back to my traditional v6. Okay, so there's one type of I'm going to call it attack, a misconfigured router perhaps. Oh, I don't know why VMware does that. I need to figure that out. VOS, is this the attacker? It is. And I want to take this guy off. Got to spell all the words. And you know what? Before I do that, as they say, always make sure, yeah, that is the attacker. Yes, definitely turn that guy off. All right. So we're going to do that. And eventually, you know, everybody will kind of go back to normal because we had also on some of these some short timers. We can look at these IPv6 interface, show adders on interface 13. And we can see that my bad addresses are going to time out in just under 3 minutes. We can see my other real normal address had a little bit longer timer value on it. So that's all good. So we've got things going on and we're having a good time. Let me show you I'm going to show you what I'm going to call a DOS attack. All right, we're going to fire it up with this guy here. I'm going to use one of those toolkits. I'm going to use the Hacker's Choice IPv6 toolkit to affect a particular change in my network. And it's quite fun to see. And I think that's going to be almost the end of time for my demo. I'm running short, but that's okay. You can kind of get the idea. These tools are great, again, from even the learning aspect. Run it like this. Build the network up the way you might want it to operate in real mode, and then fire up some of these tools. See what happens. Honestly, the different vendor OSs and the different versions within a family of OS act differently. So you cannot say, oh, if I have a DOS attack, this is what's going to happen. It will not be consistent. And you can't even say for all Windows 10 or all Windows 7 or all Windows 8 or all Windows Vista, all right, or Mac OS X or any Linuxes. You've got to understand what everything's going to do in your world. All right, this particular attack is the mode of anytime a dad test is run, answer it and say, yes, that's me. All right, so I'm going to run this test. And now I'm going to do a couple things. First off, I'm going to go into my computer and I'm going to cycle my interface so that I can effectively get a new address option. And minimize that. And let's go back and look at this and look at, I've been out there and I'm saying, well, can I have this address? Can I have this address? And it's saying, nope, that's me. Nope, that's me. Nope, that's me. So what effectively happens is I may not get a working address. Now it's kind of interesting. Sometimes in my show and tell, I get different results. All right. Again, one of those things in lab. Pardon me. I look like I have an address here and it might work. I guess I could try to ping the server and it looks like it must be working. So maybe my dad test got tired and it finally allowed me to have a valid one. Which one is it here? 9F2F. It doesn't look like it answered that one. It looks like I was able to sneak one through. There was that old EE4C one. All right. So I can, let's go look at that Windows 7 machine right quick. And let's cycle its interface. Oops, I see what I want. And we'll see what it does. Oh, here we go. I'll finally get there. Local network. Let's disable it and re-enable it. We'll go over here to our attacker. We see a number of additional addresses that are failing to pass. And if we go back to that Windows computer, Windows 7 client, and my bad. Let's look at his configuration. And it looks like even right now, doesn't even have a v6 link local address. So in this particular case, the way Windows 7, this exact version, I mean, again, you really need to understand this in a production world, that you cannot just say, oh, Windows clients will act this way. Now, if every single one of your Windows clients is configured exactly the same way, the exact same level of service patches, the whole bit, then you might be able to get away with that. But in this particular case, just even looking at two different versions of Windows, major versions agree, but we can see that I don't have a v6 link local. So for all practical purposes, I'm not participating in a v6 world. I know who my gateway is, and that doesn't matter. I don't have anything else to work with. Yet over on my client over here, I had one, right? See if we still do. I expect I will. Yeah, we still have one. So those are some of the tools and some of the capabilities of a tool. I'm going to go ahead and stop this one for now that we have out there. I did want to show, I think I have just enough time. Let me see if I have it on this computer. Sorry, I'm kind of looking through my notes here. Where is it? I may have to fire up another one to do my Nmap. I lost it. I've got one of these that I can run. Oh, here we go. Server Tools Attacker. Oh, okay. I might be able to do it here. Let me, let's get back over here. Tools Attacker. Oh, he's not. My apologies, team. Tools Attacker. I should have an Nmap one in here. We'll see if we can run it. So we're just running a basic test against our server on v6. And in this particular case, I want to find out what ports are open. All right. Again, you're not going to run big time sweep type scans. All right. You're going to, in a v6 world, you're going to run targeted scans, targeted to addressing. Like, what is the normal fourth octet of a router in a network? It's either .1 or .254. Okay, fine, it might be something else, but those are the two normals. Well, the first thing I'm going to look for in a v6 world is :1 or :254, because humans are predictable creatures. All right, we're going to try to make things easy and do it to match my v4 looking world. So my attacking, that's how I'm approaching my v6 attacking. Again, using all those very simple ways. It doesn't mean I'm going to get a hit, but it certainly knocks off a few of the easy things first. And one of the other things that I would most likely do is try to get some link local or devices that at least have a link local and perhaps have a gateway. And then I can use the link local of the gateway for the case of, in this case, the default router. So all these different kinds of attacks, whether they're, I would kind of call it, basic red team recon type attacks or whatever, the methodology that we can employ is relatively easy for the first pass. Now, after a while, things are going to get a little tougher. But we can see, looking at this address, it's a server address, and my Nmap is not up to date, so it might come up a little bit better. But at least it knows it's a Microsoft something. All right, doesn't know that it's 2012. But again, my definitions files aren't up to date. But I can see important stuff like what are the ports that are open. One of my favorite attack ports is the RDP port. And yeah, so there we have it. So Nmap, wherever you get Nmap from, right? The Kali Linux again has all kinds of utilities that we can use. So with that, I could show more things with different utilities, but this gives you a little bit of a flavor of, you could have just misconfigured devices causing grief, all the way up to purposely attacked or some type of a sweep or a scan or whatever might be going on out there. And at the end of the day, if I go back and look at my Wireshark and I kind of look and see, here's where that scan was being done, right? But if I look at this from a v6 thinking world, I'll find it. If I look at it from a v4 thinking world, this is completely missed, all right? My IDS IPS is not going to find this if it's not looking at v6, all right? If I've got just Wireshark running and no filtering going on, okay, yeah, I might see some of that stuff happening there. But I look at that, and if I've got any clue that it's a v6 address, I'm possibly going to dismiss it because I'm not running v6. We can't think that way anymore, all right? We can't. You've got to be watching v6 as much as we're watching v4. Otherwise, it's this easy to do things. So let's go look at Q&A. What say?
Sounds good, Jeff. You've got about 13 questions.
13 questions. All right.
Oldest to largest. Nobody. I've got a couple that have been +1. So look for the handshake that's got, the thumbs up with the little 1 next to him.
All right. How about one with a 2?
Yeah. Do that one.
Okay. So we've got. Do you have a link on the exact algorithm used by Microsoft? Google that. I do not have a link. All right. Or use your favorite search engine.
There you go.
But it is not a secret. The percent signs, okay, in Windows and on any type of a device, even in Linux, you may not see it as a percent, but those are the interface IDs, and we need those when we're doing any kind of link local addressing work. You have to always specify in any v6 capable OS. If you want to do anything with a linked local address, you must specify from which interface. It doesn't matter that they're on the same layer 2 domain. You have to specify. How you do that will depend on the actual OS, even on router OSs or layer 3 switch OSs, everything. Even if you want to do it through a browser link, you would have to specify the interface that you want to get to, say a web page or any kind of an application. So yeah, very good pickup on that. So there was another question. I got lost. Turning off v6 on the router, how does turning off affect the attack vector that aren't using? No, because again, it's OS by OS, device by device. Just because you're not running a v6 in your network does not mean v6 can't be running in your network, okay? That's really, really key. That's where a lot of people, I get them into these seminars, say, who's running v6 in production? Very few hands go up. And I say, how many people are running these operating systems? Everybody raises their hand. I said, go turn on a router in your lab, and you'll find out v6 will light up all over the place. We don't, my attack demo is not part of SharkFest. I have run it before in a couple different venues. It's a little bit more fun. It's a little bit like what we saw here, but it's a little bit different. I actually come through the public internet on a v4 compromised device, and I get into the inside of the network and light up v6 and navigate all around the network on v6, and nobody's watching. The main utilities is pretty much what I had on that one slide. I'll show that again just to have up and handy real quick. Give me just a moment. I'm gonna try.
While you're doing that, Jeff,
yeah.
Do you intend to share the slides on the SharkFest retrospective?
Yes, the slides will be on that site when we will get there. We will get it there.
Yeah. Cool.
Pretty much the THC and the SI6, both of these toolkits have some specific capabilities that the other may not have. The THC toolkit is a little bit, I would say, more documented than the SI6. However, the SI6 has more depth in some of its utilities. You can really get down and craft some interesting configurations for a tool to run. But those are my primary, that and just a router like I was running a while ago, that VIOS router. So yeah, lots of good tools out there. So if you're not running a router, you could possibly be a device in the middle. Yes, we can. And yeah, as that other point is, I actually want to add to my little demo, and in my attack demo, where I become the v6 router, I get all the traffic come through me. I let them go to the outside world on a tunnel through v4 on the internet, and I get all their stuff because their operating systems are defaulting to v6 where they can. Yay! Oh, this is mad scientist fun kind of stuff. Did I say that out loud? Okay. When you say unique local domain, yes, good catch on that, all right? A unique local is a routable address within, quote, your domain. It's just like an RFC 1918. You cannot route a 10 dot address to the public internet. You can try, but your upstream should be blocking it, just like you should be blocking a 10 coming into you. Same thing with those EULA addresses. It's a specific prefix. You should block it from going to the outside world, and you should block it from coming from the outside world, because they're blocking it on their side, on your upstream. But inside your world, you can use EULAs all over the place. Don't do it. It's a waste of time. Everybody goes, oh, I can't have a global unicast address on the inside of my network. I've got no security. Wait a minute. Are you thinking v4? We call that v4 thinking. Stop it. Okay. Don't use NAT as your security. Don't use EULA as your security. If you just really got to have a non-routable to the public world address, okay, fine. There's a number of blog posts that have been discussed with EULA, and it's just basically don't do it. Just be a little bit more mindful of how those GUAs work and where you're routing the GUA addresses. That's the way v4 used to be before RFC 1918. So we're kind of like back to that. The tools, actually, I think, I don't believe, at least in older Backtrack, and then it moved to Kali Linux in name. I just don't remember if older Backtrack had any of these V6 tools. And I don't even remember when it started happening in Kali, honestly, but they're there in at least the last 4 or 5 years of Kali. So getting access to those tools, you'll get a Kali Linux and load it up, and that's great. I'm trying to make sure I didn't miss anything else. Tools for blue teams, same tools. All right, to a certain degree. The other thing is you want to start looking for IDS that has V6 awareness. I actually haven't gotten to that point yet. I would like to do more research on that. V6 is not in my normal day job, so all of this is more on the fun. So yeah, some of those tools are going to have to be developed. If you build it, they may come. Another comment about address management, disable Slack and go to DHCP v6. There's actually been a lot of conversation about that recently. Most people are probably going to do DHCP v6 if they do DHCP. They are used to it. Most of the DHCP server applications, like Microsoft servers from Windows 2008 and on, it supports both protocol capabilities. So most people are going to do it. There are some operating systems, Android for one, that doesn't even support DHCP v6, period. And oh my goodness, is there a lot of arguments and conversations about that. But the bottom line is you may have to have a hybrid world. You may not want Slack, but you may have to have it in a few places. So do one or the other. It's really a little bit more of the overall design. Go get Tom Coffin's book on IPv6 address planning for a lot more detail about that world. Even if you have to come up with a plan and then redo your plan, you've probably done that in a v4 world at some point or been around that. Basically, we figure that's going to happen everywhere with v6 because of the way it operates and the way you can extend it out so far. So that DAD test, yeah, that pretty much, hopefully I just showed that basic one. Part of it is going to depend on the operating systems and how they're going to act. Part of it's going to depend on what you're running to be that answer every DAD test, right? What utility. My little example is not very powerful, but we saw some different operations there with it. So again, just about anything could be on the network. There's DHCP v6 spoofing mitigation in most enterprise class type infrastructure devices as well. So that, yeah, I may send out DHCP v6 solicits. I can block the advertisement. Yeah, the DAD test, you might find a high percentage of responses, and there may be a way to mitigate that. I said DHCP v6 spoofing, but we may need something for basically ICMPv6 type replies. The slides will be up. Minimizing the attack surface. Learn v6. That's your first thing. Second thing is watch for it. Be mindful of it. Make sure that things are not running it if you don't want it. For instance, in a few of the vendors and router and the enterprise class products, they have started to enable v6 by default. It has not been that way up until about the last year. Your mileage may vary as to which one, which version of code, et cetera, but on all your clients, it's there. You more or less can't turn it off because especially in the Microsoft world, so many of their services require it to be enabled, not necessarily used, but enabled. So really, what's the best way to not get in trouble? Turn it on and make it work. Run it in production on purpose. And then that way you won't have to worry about these things slipping through. I know that sounds very easy for me to say, but we really are kind of getting to that point. So let's see. Right, search terms of WRT. I'm not sure what that's for. Yeah, rogue router tunnel, just talked about that. Definitely. There's a couple of different v6 tunnel protocols, like IP41 is one particular tunnel protocol. There's a couple of others. I don't have them off the top of my head. So you could watch those on your external side firewall to see if you've got any tunnel protocols firing up that you're not expecting. So let's see, what else do we have? Yeah, DHCP, there's in DHCP v4, the MAC address is the unique identifier for a client. In a v6 world, it's called the DUID. It's a unique address. It's this big, okay, this big, it's huge, and it's unique, and it's not easy to track. There's conversations in the standards committees about maybe making that back to the MAC address so that people can track it from that perspective. Somebody was asking, if you want to build something in virtual, you don't need a lot. You need a few processors machine, 8 gig of RAM, and you can fire up these little VOS machines or Linux. You could fire up a number of Linux machines. You could do this on Raspberry Pis. If we can do ESXi VMware on Raspberry Pis, you can build all kinds of fun stuff on Raspberry Pis or almost any kind of a computer laying around. All right, that can run a Linux, a low end, a low footprint Linux kernel, and you can play with v6. So that makes it really easy, all the way up to the more things you might want. Even Windows, all of my little Windows VMs in here are basically 1 gig, one processor. They're not super fast, but I don't need fast. I need operations. So definitely, yeah, comment about a Raspberry Pi, pick a Raspberry Pi. It almost doesn't matter. You actually could possibly take one of the new Raspberry Pi 4s with, say, I don't know, 8 gig of RAM, and run Docker containers or even Kubernetes on top of it, and run some Linux VMs in containers, and have low footprint. So there's all kinds of different ways to build like your own little lab. Betty, did I catch most of the ones in the Q&A section? I think I did. I didn't tick them as I went, but I think I got them. So let me
yeah,
look
you
up.
actually got most of them.
Okay, I think
If
there
they're
was
still in open, I moved them to answered as you answered them. So if they're still in open, I don't think they've been answered yet. Yeah, like you've got
there's still
13
a bunch.
answered and open 11.
Yeah, but some of those I did answer. So I
Oh,
answered,
well,
yeah.
including my list.
So I'll just click them.
There you go. Yeah, click the
Okay,
third
should
answer.
have been doing that all along, I guess, huh? Yep. So every device could be a device in the middle attacker. If you're not running router code, you could still have that. I mean, yes, absolutely. Anything that sends out the packet, whether it is a quote routered or routing device, I can craft the packets with those utilities and send out a router advertisement and make things do whatever I want. Okay, so yeah, you can be a device in the middle attacker really, really easy with just a properly formatted packet, properly crafted packet. It is really, really not hard to make that happen. Whether you do Slack or not, yeah, we talked a little bit about that. It depends. It depends on the environment as to what you need. Everybody's going to respond. There's not really a way to get around the DAD test. You must do it, and somebody can respond. And I think we've hit my limit. But I think we got the bulk of the big
The
questions.
bulk of the big ones.
Thank you, everybody, for coming in to IPv6 Attack Tools. Thank you for coming into SharkFest. Have a great rest of your day and days. I guess we still have tomorrow in SharkFest. Happy Wiresharking, and thank you.
Yay!
Okay. Thanks, everybody. All right. Specs.
Oh, I'm going to be on Discord, Roger.
Is there a way to save the questions? Oh, that's what you said.
Yeah, but I took a screenshot of most of them.
Okay.
But you can save the chat if you just hit the
Yeah.
little
Yeah.
ellipsis. Yeah,
I got chat saved.
awesome.
Looks like we're still live. That's okay from my perspective.
Hmm. Well, I'm going to go ahead and jump over to Discord.
Okay. Thank you so much, Betty.
You betcha. Talk to you later.
Okay.
always know which way to go. Every path I choose is not my own. Send me a light for the night. Oh, comfort me. Oh, comfort me. Then I'll go. It'll take a lot of time to make it right. Will you still be here when I'm fine? The answer will tell me what I know. Oh, comfort me. Oh, comfort me. Then I'll go. Oh, comfort me. 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 I will follow. Call on me. I will follow. Call on me. I will comfort you. Help me, 'cause my journey is the same. Broken down and broken many things. I know that you can carry the weight of the world with you. Oh, comfort me. 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 Then I'll go. Oh, comfort me. Oh, comfort me. Oh, comfort me. Oh, comfort me. Oh,
Can you hear me?
I will follow. Call on me. I will follow. Call on me. I will comfort you.
So, good morning, or good afternoon, or good evening to everyone. I'm Betty Du Bois, and I'm here with Mike Kershaw. And I just want to let everybody know before we start that if you have any questions, just go ahead and put them into the Q&A section, and we'll be watching those. And if you see a question you absolutely love, be sure to go ahead and do a thumbs up on it and click those up, because I'm thinking Mike might answer those first. So go ahead and take it away, Mike.
All right. Hello, everyone, and welcome to the Kismet and Wireless Security presentation. So I'm the author of the Kismet Wi-Fi tool and a bunch of other Wi-Fi related tools. I've been involved in Wi-Fi security since 2001 or 2002. Kismet is over 18 years old now, so software that's old enough to vote means get off my lawn. But why do we care about this? I mean, Wi-Fi sniffing's been around since the late 90s. The first 802.11 stuff started launching around 1999. Wi-Fi is still only becoming more and more prevalent. The majority of corporate deployments are Wi-Fi now. They still do Ethernet to some desks, but I think the number of companies that do Wi-Fi based laptops and everything far outweighs that. There's also Wi-Fi for sensors and control networks, etc. So yeah, everything's moving away from wired. So why is wireless special? I mean, why do we need to have a special talk about it and special software? Can't we just capture from it like we can with everything else? Aren't there enough tools that monitor packets out there already? If only had a conference about some of those tools. But Wi-Fi is a bit of a unicorn. It's a bit special. It is truly shared media. Every transmission impacts someone. You're not just limited to your physical network like you are with Ethernet. So on like a hubbed Ethernet, everyone on the same physical network interacts with each other. But with Wi-Fi, every adjacent network or adjacent device, even if it's not part of your network, impacts the performance and integrity of your networks. It isn't Ethernet. Your OS might present it like it's Ethernet, but it isn't. Knowing that a network is present based on advertisements that the network is around isn't the same as knowing what's really going on with it. So you can know that you have 10 networks near you, but you don't know that they're heavily in use, if they're idle, etc. If anyone remembers their OSI model, the 7-layer model, you're going to really care about layers 1 and 2 all of a sudden. Most of the Wi-Fi issues and issues with capturing happen down on layer 1 and 2, the physical and data link. So if you want to discover Wi-Fi networks, there's several ways to detect them. The traditional way would be scanning mode, where it detects it based on advertisements. So the network beacons out, I'm a network, here's my name, here's my encryption options. You can detect those. That's how your operating system finds the list of networks near you. But it's not packet capture. It won't show you things like clients, it won't show you data traffic going on, and it won't show you problems that are happening on the network in that regard. Similarly, some enterprise access points have assisted capture, where they can discover APs near them. So you can do, find interfering APs and automatically list APs and pick channels. That's still looking for advertising access points, not capturing the packets. We want to see what's actually in those packets. So how do we get them? We can open the Wireshark. We can open the Wi-Fi interface in Wireshark normally. You'll get some sort of packets out of it. So if you just do a capture from your Wi-Fi interface in Wireshark, you'll get something that looks like this. Wait a minute. Yep. So we don't want that. The OS is presenting the Wi-Fi card as a traditional Ethernet device. That's because the operating system and the rest of the stuff on the network stack on your system know how to work with an Ethernet card. The data packets on Wi-Fi can hold the same content as Ethernet, so this makes sense. But this capture will only get as data packets, usually only from your single session, possibly broadcast depending on your driver, or it's a little random what happens. There's a lot more to Wi-Fi than just the data packets, though. And there's even more to Wi-Fi data packets than just the data you get in them by capturing in this mode. So what we really want is something where we get the full Wi-Fi packet, where here we can get the signaling header, radio information, low-level control information, and then after all of this comes the data packet that was all we could get before. So how do we get to that? With traditional network cards, there's promiscuous mode. It just turns off the packet filter and you get all the packets. So you still get, but they're all Ethernet packets. For Wi-Fi, we need a whole other mode of operation. So Wi-Fi calls that monitor mode or RF-MON. The operating system won't understand what's coming in anymore because it's going to be raw 802.11 or 802.11 with signaling headers. But Kismet and Wireshark and other tools like that do understand it. Monitor mode isn't part of the official spec, but lots of drivers support it. Unfortunately, there's a bunch of exceptions in strange behavior because of course there is. Why would this be simple? So the fun part, we need an operating system that supports monitor mode. We need a Wi-Fi card with firmware that supports monitor mode. We need drivers that support the monitor mode for that card. That's a lot of moving pieces. You might think that sounds a bit intimidating for getting the right stuff, and you're right, it can be a real hassle. It means the specific chipset of the card matters. The brand doesn't necessarily matter. The model doesn't necessarily matter. A lot of manufacturers, especially of consumer gear, will change what's inside the card without changing the product name. They won't change the model. So like a TrendNet 111 has 3 different revisions with 3 completely different Wi-Fi chipsets inside of it. And what we care about is the actual chipset that's in there. So you need to do additional research to find out exactly what's in it. And it often means buying from companies that advertise what chipset's in their card. Other problems with monitor mode is it is not a standard, so it's not required. It may not be consistently implemented. It might not be implemented at all. The common failure modes for it, you might think you're going into monitor mode, you just get no packets. You might get only data packets and none of the other types. Your packets might be corrupt. You might get bogus packets. It's easier to get into monitor mode now than it was 10 years ago or so, but it still's got its challenges. Kismet tries to solve this automatically whenever possible. So in general, Kismet, if it can detect your cards, will bring them up into the correct mode and configure everything already for you. So we said one of the problems is missing the firmware modes for monitor mode. This happens a lot on mobile chipsets. Unfortunately, mobile chipsets are also found on things like the Raspberry Pi. So as shipped from Broadcom, the drivers for the Pi do not have monitor mode implemented in the firmware. There's some projects to replace missing monitor mode firmware. So Nexmon solves it for Broadcom, where they actually reverse engineered it and reinserted monitor mode instructions into the firmware for the card. With bogus packets, Wi-Fi packets will have a checksum, and you'd think that would be enough to solve this. So since Wi-Fi goes over the air and there's a lot more chances for interference, it's heavily checksummed in ways that Ethernet isn't always. So you'd think that would be enough to solve this problem, but some drivers just don't report the checksums at all. They're just not included for no good reason. So we have nothing to validate against. Some only report that the checksum was valid. They don't give you the checksum data. They just say, we think this packet was valid. So if the driver implements that check incorrectly, there's no way to compare the data for your own purposes to find out if you're getting valid packets. And some packets report a checksum, or some drivers report a checksum, but they calculate that checksum from the data in the buffer, which means it has no relationship with the actual packet. It's just, sure, we checksummed whatever random garbage we got, so it's okay. So that defeats the entire purpose. To complicate things even further, Wi-Fi keeps evolving. So 0 to 11B, G, A, N, and then we ran out of letters. So there's AC, AX, and so on. Each iteration of the drivers have significant differences and challenges, both in what kind of packets are transmitted, the physical way packets are transmitted, et cetera. And generally, the newer and faster the Wi-Fi standard is, the harder it is to capture because it's got more information going at a higher data rate, which means the effective signal level is lower. And it means that the encodings are often more challenging to receive. So can you see everything out there? You can't. As a passive observer, it's impossible to get guaranteed total coverage of a channel. Unlike Wi-Fi, you can't just plug into a span, or unlike Ethernet, you can't just plug into a span port and get every packet on the network. Clients and access points may see packets that you never will. And because you're a passive observer, you can't say, I didn't see that packet retransmitted. It's just, you won't see it. Compounding that is there are many channels. There's localized interference. So it might be traffic on a different channel than the one you're looking at, or there might be, Bluetooth or a microwave oven or something that disrupts the signal near you so that you miss packets, but the rest of the network continues to operate with them. So ultimately, you just have to accept that when you're monitoring Wi-Fi, you will not have 100% coverage the way you might with traditional Ethernet. So sniffing the older stuff, 11B and G and 11A, they're the oldest of the common Wi-Fi standards. There was some pre-11B stuff, but it wasn't widely sold or deployed. These are fairly easy to sniff. They're simple encodings, they're slow data rates. So it's easy to get the symbols, and it's easy to hear them because they're effectively speaking, loudly and slowly. It's one antenna transmitting. If you remember the old WRT54 access points, or if you picture a traditional access point in your head, you'll have the two little Wi-Fi antennas sticking up out of it. Even if you've got the two, only one of those is active. The second one is to help receive packets better. So there's only one transmitter. If you're in range, you're pretty much going to see those packets, but it's really uncommon to find legacy 802.11b now. More modern Wi-Fi, 11N, AC, and AX, use a technology called MIMO, multiple in, multiple out. What that really means is that you have, if you have three antennas, then you have three systems coordinating transmission and reception at the same time by doing all sorts of neat radio encoding tricks to effectively create multiple streams of data that recombine to form the packet. This means more bandwidth. This is one of the main reasons that modern Wi-Fi is so much faster. It means better resilience to interference, which is also why Wi-Fi is much more reliable now than it used to be. But because now you have multiple streams of data going out, bouncing off things, coming back and recombining, it's much harder to sniff because where you're physically located suddenly impacts whether or not you see the packet. So the client the packet is meant for might see it perfectly fine because it's bouncing off a filing cabinet and a wall, and the two streams are combining fine. But if you're 20 feet away, you might not see that packet happen at all because you missed part of the stream, and the network will never retransmit it because the proper receiver has already gone and acknowledged it. So it can be much more challenging to sniff data packets from the newer networks. And now with 11AC and AX, there's beam forming, which is next level sci-fi tech, where multiple antennas that would operate in any direction create a signal out of phase so that each antenna sort of creates the signal in sequence, and it effectively makes it a directional antenna out of multiple non-directional antennas. It means the access point can effectively aim the signal at a user, which increases the signal quality and the bandwidth and decreases the interference to other users. But it's terrible for sniffing data because now if you're not part of that beam, you're even less likely to see enough of the packet to be able to decode it. Also, sniffing the newer protocols requires the newer hardware. It's sort of an obvious statement, but you might see the beacons in the advertisements saying, here's a network, it's 11AC. For backwards compatibility, those are sent at a more common data rate where older cards can still see them. But so you'll see that the network is present, but you'll never see what's happening on it if you don't have a card that's of the same standard. So you'll see that 11N network exists, but you won't see its data with an 11G card. Similarly, you might see that an 802.11ac network exists with an 11N card, but you won't be able to see what's going on in it. So the newer Wi-Fi standards are much more complex, which means they cost more to develop. The licensing is more restrictive because more patents are involved now, which means there's fewer companies making it. So we went from probably 20 different varieties of 802.11b card and G cards that could sniff to just a handful of 11AC cards that can sniff, 3 or 4 at most. And as far as I know, there's one single 802.11ax card, the Intel AX200, which is capable of doing monitor mode. So what are the options that we have for capture? It really depends on your operating system. For OS X, you can capture with the built-in airport. So you can capture up to 802.11ac, and I don't believe there's an AX one yet, but I would assume that when there is, it will probably also work. Nothing else on the Mac can capture raw packets. There's no generic USB monitor capability due to a lack of drivers on OS X. So you can't buy like an 11AC USB card, plug it in, and have it work. And Apple is continually making it harder to add out of kernel drivers, unfortunately. Catalina has greatly restricted this, and I believe Big Sur is going to restrict it even further. Good for security, bad for adding capability like this for OS X. For Windows, Case made the ARP cap, but I believe that's been end of life. There are some commercial capture products. You might think, well, there's WSL, Windows subsystem for Linux. Unfortunately, that can't talk to USB. There's WSL2, but that's based on Hyper-V, which is Microsoft's virtualization layer, which doesn't have USB support. So there's no way to actually interface to the hardware. Sometimes if you're on Windows, you can use a VM and run it in there, but we'll talk more about that. Linux is by far your best chance. Many chipsets work in Linux. I would even say probably most chipsets work in Linux. Of them, Intel, so the IWL Wi-Fi stuff found in most laptops works quite well with the modern kernels. There is a chipset from MediaTek, the MT76X2, has been added in recent kernels. It started showing up around the release of the 5 kernel, and it works really well. It does 11AC, it's USB, it's probably the best so far to get working. Older Atheros cards, the Ath9K 11N work great. Raspberry Pi with patches, you can use the built-in cards. So you can use small embedded systems for capture and feed those packets elsewhere. You could also use a live CD if you have a laptop that's running Windows and you don't want to install Linux fully onto your hard drive. Cards to avoid, there's a chipset called the 8812, and it's found in hundreds of different brands of cards. It's very cheap, $5, $10 cheap. It's unfortunately also very bad. The drivers are not, probably never will be in the kernel. They're always going to be out of the kernel because they're so bad and non-standard that they're effectively unmergeable. They tend to work or not work on any given git commit, so it's almost impossible to reliably get them. So if compiling your own kernel drivers and debugging them isn't for you, avoid this chipset. And you can find out what chipset's in the card usually by the manufacturer page or with Google. Similarly, the modern Atheros Ath10K, which is a higher end 11N or 802.11ac card, has buggy firmware that reports just floods of bogus packets. And because the firmware is closed source, there are no fixes available for it. So if you wanted to try Linux, many distributions have a live version. So, live CD, live USB that can boot without modifying the hard drive. Some are directly built around this. So Kali and Pen2 are good examples of distributions meant to run without modifying your hard drive. You can install them normally, or you could just run them off USB. And it's typically a quick way to get going, but it might not have the most current versions of the tools. And depending on how your laptop's configured, you might have to disable secure boot to be able to boot a system off USB, and that might interfere with your Windows file encryption. So just be aware of that when you go into it. Virtual machines sometimes work, but they're generally discouraged because they can be really funny. USB devices may work via USB pass-through. Wi-Fi cards typically do. Other cards often don't because of how the Windows USB driver model is written. It's very strange. If you have a PCIe or a PCI card like the Intels or the Atheros, they will not work because there's no way to pass that to the virtual machine. So if you're going to try it, your only chance will be with USB, and it might be a little flaky. I've seen success with VMware on Windows. I've heard that VirtualBox can work. Both of them on OS X tend to have problems, and often the community will refuse to help people with VMs because of prevalence of issues. So I've seen them work, you can get them working. I've helped people get them working. But if you, for example, like go to the Kali or Pen2 people and say that you want to run it in a VM, they probably won't be very receptive because there's so many problems with it. Your other option, though, is remote capture. So Kismet can support capturing from a Linux box over TCP. So any supported device, a Raspberry Pi or a little OpenWRT router running the remote capture code for Kismet can feed packets to OS X or Windows. So you can effectively use a little Ethernet connected device and use that to capture packets when you couldn't connect to a USB device. So when is it worth all this hassle, since we've just spent 15 minutes talking about how it's inconsistent and a pain and tricky to find? You don't need to worry about this if you're looking at, say, analyzing data traffic from your own laptop. So if you're trying to debug at the application layer, if you're trying to debug HTTP or an application traffic, things like that, that's just data on Ethernet. So you can just capture it from Wireshark like you would normally. If you're looking at broadcast and multicast on your network, MDNS and whatnot, that should typically be capturable without monitor mode. Just open your interface in Wireshark. If you're able to capture network wide at the switch, so if you're hitting like a span port and you're grabbing all of the user traffic from your Wi-Fi network, you don't need to worry about the Wi-Fi packets. You just care about the user traffic. You don't need to worry about any of this. However, you absolutely do need monitor mode if you want to capture the Wi-Fi layer. So if you want to see hidden access points or deep information about the access points, if you want to see clients and what the clients are doing and what they're sending, in addition to what data is actually crossing your network, you can look for that. So if you want to see, clients doing peer-to-peer traffic like Wi-Fi Direct, phones can share Wi-Fi packets between each other without talking to your network at all. So that's a path of communication that your main IDS or capturing off your network side of things wouldn't see. If you want to monitor for people attacking your network or some denial of service conditions, or if you want to audit or attack WEP, WPA, WPS, other standards like that, you need the raw Wi-Fi packets. So you need to care about all of the minutia of getting the right interfaces going. So some of what Kismet does. So Kismet's designed to do several things in the Wi-Fi space. So it's designed to manage the different cards. It'll handle all the supported card types on all the supported operating systems. So primarily OS X and Linux. It'll run in WSL, but WSL is really just Linux, so doesn't really count. It'll deal with the quirks of getting them in a monitor mode automatically. There's a couple hundred lines of code that just match different drivers and try to accommodate their weird quirks. It'll keep the operating system from breaking the setup. Network Manager in Linux really likes to take over the Wi-Fi configs, even when you have it set up in monitor mode, and then reset your configs all of a sudden for you. So Kismet will automatically stop that from happening. And it will deal with handling all the different channels. So Kismet was designed to basically enumerate the network devices, access points, clients, and devices and their relationships between them. So it's more network and device centric than it is packet centric. For all the other functionality, it can talk to any other tools like Wireshark that handle packets. So it'll generate, PCAP, PCAP-NG, various different radio headers on the packets. So Kismet's been around since around 2001. And you might be used to it looking like this, especially since a lot of distributions don't update that often. So this is how Kismet used to look. Since then, Kismet's had a really significant rewrite. It's now got a web-based UI. There's REST and API and JSON endpoints integrated in, so you can pull the data out over just standard web requests. There's a new logging system, a new common log file. You can get a live feed of packets that it's seeing just over HTTP, and you can do remote capture as if it were local. So, some screenshots of the new UI. It's all web-based and fancy and Ajaxy. And you can view the network details and see graphical representations of the different types of packets and data in them. And you can manage the data sources. You can get graphing of all of the historical data and all sorts of other features you'd expect, in a more modern application. Pardon. So sometimes people try to pitch it as Kismet versus Wireshark, but Kismet and Wireshark are completely complementary. You'll want to use both depending what you're doing. Wireshark is very packet oriented, while Kismet is network and device oriented. So if you're doing traditional packet capture, you're doing analyzing traffic, you'd probably plug into a span port on the network, look at the packets. Maybe you have to worry about VLANs and where packets are divided there. But if you're doing wireless PCAP, you need to worry about what channel is the traffic on. Is it user to user, or is it going through an AP? Are you trying to debug that there's another access point causing interference? Is that keeping you from seeing packets? Did someone bring their own access points from home? Is the problem traffic from an access point you didn't even know was in your office? Are people doing BYOD hotspots where they put their phone into hotspot mode to bypass the corporate restrictions? For Ethernet, basically has one type of packet, which is Ethernet. Wi-Fi has around 45 different subtypes of packets. So Kismet looks at all the contents, just like Wireshark does, to determine the packet types and contents, but then it sorts them into devices, networks, connections, and so on. So the same Wi-Fi device might be talking to multiple networks over the course of several minutes to an hour. So it'll track the interactions between devices. They might be connected to your own access points. They might be connected to fake access points. They might be connected to BYOD stuff that someone brought in from home, and et cetera. And all of that needs to get, tracked and related to each other. Kismet can include geolocation from GPS or some protocols that have location info built into them, and it can convert multiple packet types from multiple radios into one record. So if you have, 3 different Wi-Fi cards seeing one client, it'll show up as one client instead of 3 different copies of the same packet. So, if you look at a packet at a network in Kismet, you'll see, signal levels, locations, information about the network that's being advertised, the SSID, various usage patterns, and then clients that it has seen connected to the network, and the time frames that they've been connected and active in. So it's a representation of packets over time. The advertisements and beacons define the network name and encryption. The other information, they can indicate how many clients are connected to the network, and give you other information. 802.11ac and AX information is in the beacons. And the clients are mapped based on their traffic over time, which lets us do trend-based security alerts when these attributes change. The same interaction seen from Wireshark has, you might expect it, where it is multiple packets. So of here we have, the same networks advertising themselves over and over again. Some data packets in there, but there's no immediate way to visualize the relationship between, the packets and what devices they represent and how they're interconnected, which is where Kismet makes more sense for some views. So you can get all the same info and even more info from each packet in Wireshark, but it's presented really differently. So Wireshark is really good for detailed packet analysis, which Kismet isn't really designed to do. Kismet's meant more for representing, the devices that are out there and then letting you drill in and get the packets to analyze. So like we said, Ethernet has one fundamental packet type, Ethernet, and it contains data. And that data might be IP or TCP, UDP, or various things, but it's all Ethernet packets. Wi-Fi has 3 primary packet types and something around 45 sub-packet types under those. So there's management packets that define the network, so beacons. They advertise the network name, encryption options, and things like that. Control access. Management packets also control access to the network, so probes and responses that a client probes to be allowed into a network. The access point responds that it's allowed to connect. And all of these packets can contain nested lists of complex data, which contain all the information about the network or how the client is attempting to connect and what attributes it's looking for. There's also control packets. They're typically very short. Often they only have 1 MAC address in them. They're used for collision avoidance. They're used to say, I'm going to transmit a big packet. Nobody else talk on this channel. They're used to confirm the data was received correctly. And then finally, data packets look like essentially the traditional Ethernet frames. So they can be L2 encrypted with WPA. They could be L3 encrypted. So if it's a VPN or an SSL or whatnot, they could be both encrypted with WPA and running a VPN. So to figure out what's going on with the network, we need all of these packets combined. If you don't have management packets, you won't know what networks are present. You won't know, clients are trying to join networks. You won't be able to see hidden networks. If you don't have the control packets, you won't be able to see hidden nodes. You won't be able to see some denial of service attacks. You won't be able to see, problems where clients aren't able to reserve time on the channel, et cetera. And without the data packets, you'll have no content to see what's happening. Now, we've mentioned channels a few times. You can see all of the channels some of the time, or some of the channels all of the time, but you can't see all of the channels all of the time, as P.T. Barnum famously said. But of course, don't trust every quote you read on the internet. So Wi-Fi breaks up the available radio space into channels. Sometimes the channels overlap, sometimes they don't. On 2.4 gigahertz Wi-Fi, depending on the standard, some are 22 megahertz wide and some are 20 wide, but they're only 5 megahertz apart, which means each channel has significant overlap into the channels that are next to it. So if you're sniffing on channel 6, you could easily see packets on channel 3 and sometimes even from channel 1, which is why when you're doing a network deploy, typically channels 1, 6, and 11 are the only channels considered to be non-overlapping, if you've ever seen that when setting up networks. This gets even worse when you introduce wide channels for 802.11n. But on 5 gigahertz Wi-Fi, there's many, many more channels. There's also 40 megahertz channels and 80 megahertz and 160 megahertz. So this is a challenge because the Wi-Fi radio is designed at a fundamental level to tune to a single channel and to be able to very strongly exclude other channels. You don't want other frequencies bleeding into your signal because that will mess up your ability to see the packets. So you need very strong filters on that, but that means you won't see adjacent channels typically. Often they can only tune to one mode. So if you're looking at a 20 megahertz channel, you won't see packets on a network that uses 40 megahertz or 80 megahertz. And unfortunately, if you're tuned to an 80 megahertz channel, you won't see all the 20 megahertz channels within that range, just because of the way the firmware is written typically. If we want to see what's happening across all of the available Wi-Fi in an area, we need to have many radios or we need to change those channels quickly. So it's a trade-off. You can either see a little of every channel, a lot of a few channels, or most of a single channel. Like I said, you can never capture all of the data on a channel, but you can see most of it if you don't hop at all. So this is like trying to listen to all the songs that are on the radio by leaving your stereo in seek mode. You'll hear, 3 seconds of a song at a go, but you won't ever hear the whole song. And more channels means less time spent on each channel or more hardware running at the same time. So we have, 802.11b has channels 1 through 11, and G has 1 through 11. Some parts of the world have, 12 and 14. So we've got, 13 channels or so to worry about with a lot of overlap. It's pretty easy to cover all of these. Then 802.11a came along. So now we've got 38 more channels. And if you notice the gaps in the numbers, so it goes, 36, 40, 44, 48. They're further apart, which means they don't overlap with each other. It's much better for signal. This is why, 11A networks and 5 gigahertz, one of the reasons is that it performs better is they don't overlap as much or at all in some cases. Better for signal, worse for sniffing. Now we have 4 times the number of channels we need to look at. Then we have a 802.11n. Well, that's a lot more channels right there. Yeah. So how did we get to 64 channels there? That's because 802.11n added 40 megahertz channels. And you can have a 40 megahertz channel where the extended channel stretches above or below the traditional channel that you're already on. So now you need to look at channel 1, but also channel 1 extended upwards to HT40 plus. You can look at channel 6, but also channel 6 extended downwards and upwards. So now there's 4 channels where before there were only 2. Now we have 802.11ac. Oh boy. So we have 20, 40, 80, and 160 megahertz channels. And on newer 802.11ac, we even have a mode called 80 plus 80, which means 160 megahertz that aren't all in a row. So now there's even more permutations. And within each of those larger channels, they can have multiple control channels within, which means we then have to look at, 4 different control channels within 180 megahertz channel. So suddenly one channel becomes, 7 that we have to tune to. And earlier this year, they just added more Wi-Fi spectrum. There's not much public hardware that supports it yet, probably not until about next year, but they added another 1.2 gigahertz of spectrum. That's more than all of the 2.4 and 5.8 spectrum that's currently available combined. So it's probably going to be a combination of many very large channels for very high bandwidth future protocols and many smaller channels. So the number of possible channels to tune to cover all the available Wi-Fi spectrum is going to explode once this goes more commonly available. And there's even more to add into this. 802.11 AX adds subchannels where it will take a channel and split it and give each user of the AP a smaller piece of the bandwidth, so they can have less total speed but more consistent normal speed for video streaming or VoIP or things like that. So it'll be great for Netflix and Zoom, but much harder to sniff. And there's devices that do non-standard modes. Atheros defined 10 megahertz and 5 megahertz channel widths as well. So now we have 4 channels for every possible original allocation. That if you want to cover every potential method of Wi-Fi, you need to look at them as well. So we need to change channel, and we need to change it quickly to see what's going on. We have 2 choices. We can either hop faster, but at some point there's a limit. Either you're going to be on a channel for less time than it takes for a packet to be transmitted, or more likely the operating system is just going to give up and not set channels that quickly. Or we need to add more radios, which adds It adds more demand for power if you're running off battery. It adds more cost. It adds more antennas. It adds more physical space, and it adds more conflicts in the operating system. Where if you suddenly have 10 cards trying to do things at once, the operating system might not take too kindly to that. But you can add a lot of Wi-Fi cards at once if you really want to. So Kismet's designed to handle this. It can run as many network cards as your operating system can handle. And if you use the remote capture built into Kismet, then you can run many, many, many more. The practical limits are after about 4 cards on one system, the kernel tends to have a bad time. Typically because changing channels on a Wi-Fi card takes a much longer time than most other operations. So if you're hopping on multiple cards, each one is going to start trying to lock the Wi-Fi system, the USB system, the networking system, and then also deal with interrupts for sending complex commands to change the channel, which means that after about 4, you start getting funky results, cards start timing out, the kernel might crash completely. With remote sensors, since you can effectively do 4 radios per sensor and send them over Ethernet, you've got a significantly higher limit for the number of devices you can sniff with on one Kismet session. You'll still be constrained by the CPU and RAM of the system processing the packets. I wouldn't recommend trying to send 12 Wi-Fi cards worth of data to a Raspberry Pi. But if you send it to a MacBook or a other laptop, then you have pretty good results. So one of the things Kismet tries to do is it optimizes the channel hopping. So we don't want to hop from one adjacent channel to another, especially on 2.4, but just in general. So it will scramble the channels so that it always hops at least the overlap distance apart between them. So if you have, one card hopping through channels 1 through 11, it won't go 1, 2, 3, 4, 5. It'll go 1, 6, 11, 2, 7, 9, or something like that, so that the overlap will help get more coverage out of it. Kismet will also take the channel list and split it between the cards, so that if you have 3 cards with the same supported channels, instead of them all looking at the same channel at the same time in lockstep, it'll split it apart so they'll look a third of the channel range apart from each other. So again, maximizing how much spectrum you can cover at a time as best as possible. So there's some crazy capture setups out there. The Wi-Fi Cactus was demoed at DEF CON. It is 25 Hack5 Pineapple Tetras. So each of them has 2 802.11 ABGN cards. So it's 50 radios capturing packets at once, all sent to a Intel NUC. And he reported that he was seeing over 500,000 devices in a single session of Kismet at DEF CON. And he was filling a 2 terabyte SSD every 2 hours with packets. And he had to lug around a lead acid car battery to power all of that. So this is the Wi-Fi Pineapple. And each of these is a Pineapple Tetra with 2 radios, so 4 antennas per. There's also a company, Alftel, who makes very interesting radios. So they make Thunderbolt chassis with PCI expanders and antenna combiners. So this is probably about $10,000 worth of radios in this tower here. And it is 64 802.11ax radios on one Thunderbolt 3 chain, all feeding into one Kismet instance. So they're able to cover, 64 of the 190 channels simultaneously. This is also my own mobile monitoring system in my truck, where it's an Intel NUC and some antennas on the radio, just for data gathering. You can also stick a bunch of different radios in a portable rack, which is what I did for demo. So this is a bunch of 802.11, some custom radio stuff, and some Bluetooth capture. Kismet will also scale down to be super portable. So this is an Intel Compute Stick. It's sort of meant to be a roll your own Chromecast. So it's pulling, 3 watts, but that's a quad-core Intel processor with, I think, half a terabyte of storage in it. And people have also made some setups that are much less portable, I'd say, charitably. This is one of the Wi-Fi Village guys that takes it to various HackerCons and their setup. So yeah, Kismet will run on anything from a single core OpenWRT system with 256 meg of RAM up to however much resources you have to throw at it. I know people who've thrown, i9s with 64 gig of RAM, just because they want to have very large single sessions. As a rule of thumb, you could expect, about 25 to 40,000 devices per session per gig of RAM, and more CPU always helps. But these limits, per running session. So if you want to run it on something like a Raspberry Pi 4 with much less resources, you could just script it to automatically restart itself every hour, and you'll get a new log file and stay well within your CPU and RAM budget. Kismet also has device and log timeout options, so you can have a long-running sensor that doesn't keep everything in RAM. So you can query it and see what's going on, and then it will automatically purge that backlog over time. So you might have seen a bunch of different antennas on the setups there. What antenna you pick matters. You need to pick the antenna based on what you want to do. There's a lot of bad marketing out there for antennas. There's a lot of cards on Amazon that they go, oh, have this 2-foot tall antenna, which is almost certainly not what you want. There's always a trade-off because antennas don't add power; they can only shape it. So you can't get more signal. You can just get more signal in a certain direction. So antennas come in two basic types. There's omnidirectional, which is the antenna is effective in all directions, hence omni, or directional, where it's most effective in a single direction. And typically, if an antenna is being called directional, then it is usually 180 degrees down to even just a few degrees of sensitivity in a specific orientation. So if you're going to build a system with your own antennas, you want to learn to read antenna charts. All reputable antennas should have a chart provided that show their power in their advertising material. Typically, the chart is just it's shown as a horizontal and vertical gain, and it could be labeled horizontal and vertical, or elevation and azimuth, or just X, Y, and Z. So, for example, here's what the graphs of a highly directional antenna would look like, where you can see that on the back of the antenna, there's almost no signal. And it's all concentrated in effectively one direction, both in the horizontal and vertical. So if you took that same plot and looked at it in 3D, it would look something like this, where behind the antenna, there's almost no signal, and then the greatest concentration is in front of it. So physically, an antenna like that might look like this, kind of like the old TV aerials. They're called Yagis. They're also called sector antennas, or other things have similar characteristics. You might see antennas that look like this. That's effectively the same mechanical antenna inside, and you would have a similar effective pattern. So you wouldn't want to use this if you were looking for all the Wi-Fi in an office building, because this would completely exclude anything that's behind you. But it would be great if you're looking to monitor something far away, or use it to find what direction something is in, because it limits it to only see in that direction. Versus an omnidirectional antenna, where a similar plot, but looks extremely different, where the horizontal coverage is almost 360 degrees equal, and the vertical coverage is also very, very widespread, with a couple of interesting characteristics, because this type of antenna basically looks like a donut, where right on top of it is the least gain, but then spreading out from it like a donut or an apple shape is the most effective radiation pattern. And this would be what you typically find on your access point at home or in your laptop, embedded inside the LCD panel, because you want the most wide coverage possible. You don't want it to limit what direction that goes in, because people will put the access point wherever they feel like in their house. So in 3D, it looks kind of like a torus or a donut, where it has great coverage in all directions except directly above and below. So they look like this. But remember, more gain isn't always better. More gain, some people say, that's what I need, but not always. So the trap that people might fall into is, the marketing on Amazon and other sites, where they go, here, have this 18 dB gain antenna, which is ridiculous. So, it's a silly level of gain. So we look at those same graphs again. Before, the vertical was almost the entire range. As you increase the gain, the donut gets flatter and flatter and looks more like a disc or frisbee, which means it's less and less effective above and below where it's oriented. This could be as low as a few feet or less of vertical range. I've seen crazy high gain omnidirectional antennas where if you were, if it was on a table and your laptop was on the floor, it could not see that network at all. Or even just if the access point was up on a shelf versus where your antenna was, you wouldn't see it. So randomly increasing gain isn't going to necessarily help you in most cases, which is, again, why access points and that stuff come with much more modest antennas, 2 dB or 5 dB gain instead of 18. Also, if you're taking your own antenna, if you're doing it for Wi-Fi, you need an antenna designed for Wi-Fi. It needs to be 2.4 and 5.8 gigahertz. It needs to be 50 ohm, and it needs to have the proper connectors. Any antenna you buy labeled for Wi-Fi will meet these characteristics. However, if you have older antennas for CB or TV or ham radio that are not what you want, even if you could get the connectors to fit, it won't perform well and could even damage your radio. So just make sure the antenna you're getting is designed for what you're using it for. So we've talked exclusively about Wi-Fi now, but Kismet can do more than just Wi-Fi, and there's a lot of other interesting things out there in the airways. So if you want to capture them, you need either a radio specifically designed for that protocol. So if you want to capture Bluetooth, you probably need a Bluetooth radio, or you need a software-defined radio and appropriate software to run it. So Kismet can handle non-Wi-Fi data now. It can handle other radio packet protocols. It can handle stuff that isn't strictly packets. So there's a lot of things out there that don't have a real standard because they're just, what a company used to make a wireless light switch or something. It's really hard to get a PCAP definition when it's essentially a manufacturer one-off, but with the right hardware and software, you can still decode the packets. So for SDR, software-defined radio. So if you have, traditional commercial radios, Wi-Fi or Bluetooth or whatnot, they're designed for one thing. They don't take a lot of power to run. They don't take a lot of processing power to run because it's all built into the chip. They have dedicated chips that can do Wi-Fi. So you have a chip in your Wi-Fi card that is the chip that talks Wi-Fi. But it's only able to talk Wi-Fi. It can't, your Wi-Fi chip can't handle the Bluetooth protocol, even though it's on the same radio band. And it certainly can't handle something on a different radio band. So a software-defined radio is a generic radio digitizer and RF front end. So it can handle, air quotes, any protocol if there's software for it. The catch is it's very power hungry. It's incredibly CPU hungry. They are very expensive, usually compared to a, mass-produced Wi-Fi card. The radio usually isn't as good because it's seeing much more than just Wi-Fi. So if you had an SDR that could cover Wi-Fi and, a gigahertz in either direction, then it's not going to be as discriminating as something that's got very strong filters that can only see the single Wi-Fi channels. Also, software for SDRs is quite hard to write. And a lot of it that's out there is something I jokingly call gradware because someone wrote it for their grad student project and then graduated. And now it's still out there. It's like, oh, well, you can maybe use it, but it probably won't work with anything modern. Different SDR hardware has different features. So if you're looking at it, you'll typically see, the bandwidth, which indicates the amount of data it can capture at once. So, Wi-Fi is 20 megahertz wide. Most SDRs top out around there. So you can see theoretically traditional Wi-Fi channels, but you would need a much more powerful SDR to see 802.11n at 40 megahertz wide. And forget about, 11AC at 160. You can also buy SDRs based on the range, the amount of spectrum it can cover. So it could do, 300 megahertz to 3 gigahertz, which would cover a bunch of interesting industrial networks, and then lower Wi-Fi 2.4, but not 802.11ac at 5 gigahertz. So typically the more range it covers, the more money it will cost, and the more resources you need to cover that range. There's also the sample size. The cheaper ones report in 8-bit, the more expensive ones report in 16-bit. Typically, this is less of a concern because you'll be buying based on bandwidth and range rather than sample size. Some of the more advanced ones have, multiple radios operating in MIMO, whereas the more cheap ones have just a single radio, so you won't be able to do MIMO reception. And as you add more features, of course, you add a lot of money. It's very easy to add up to thousands or tens of thousands of dollars worth of SDR radio. But it's not all doom and gloom. There is at least one cheap as dirt SDR option. It's called the RTL SDR. It's designed off a tuner meant to receive European DVB terrestrial TV. It can still receive TV, but people figured out how to hack it to return raw radio samples. So it's not a very good SDR, but it is a very, very cheap SDR. It's limited on as to what spectrum it can see because it's designed to receive these TV signals that aren't up in 2.4 gigahertz. So you can't see things like Wi-Fi or Bluetooth with it, but you can see a lot of other things. How cheap is it? One of the better, more reputable, more expensive models is $29. So, and you can get them even cheaper, but I would recommend, around $30, you'll get a decent one. It is a crap device, but for $20, a crap device goes a long way. It is a great way to get into SDR. It's a challenging field. It can be tricky to set up, but it can be really fun to detect networks or other devices that aren't Wi-Fi and whatnot, or learn how to write decoders for radio protocols. So this is a good way to get your feet wet in that and see if you want to pursue it further or if it's just too complex and flaky to be interesting. Kismet can use it for a number of things, or you can use a bunch of them at once for multiple protocols. So some of the protocols we can capture with a $30 RTL SDR is power meters. Some implement power monitoring so that the power company can read them from the street. Kismet can also decode them. So here's 2 power meters near my house, and I can watch my power consumption tick up. Weather and temperature can be received by them. A lot of weather stations use 433 megahertz, which is another public band, to link to the display inside the house. Same for the wireless thermometers, where you have 4 thermometers you distribute around your house and 1 panel that shows all the readings. So we can pick those up and see them. So thermometers like this. So for $10, you can throw thermometers all around your house and then watch them all from one location and log them with Kismet and pull the data. So we can see, temperature and humidity pulled off of them. There's a protocol called ADSB. The FAA now mandates that planes have an active transponder that sends their registration info, the call signs, altitude, direction. This is how sites like FlightAware work. They have this huge monitoring network of people who monitor these signals and automatically contribute them to the database. So Kismet can pull these out too, where we can see, airplanes flying by, which is pretty fun. So you can plot, airplanes that are near you, what direction they're headed, their altitude, and all of that. I think the best one I've seen is one of NASA's private jets flew by. So the signals coming out of the SDR is, too complex to go into in any great detail, but it's called IQ data, which is the power and the phase of the data, which can be used to decode the radio signal. It's really complex to identify packets among the noise, and this usually takes a lot of CPU. Typically, any SDR thing you're going to do is going to use 100% CPU. So just plan for that. So Kismet can also detect Bluetooth. It's much harder to sniff than Wi-Fi because it does frequency hopping, and there's not that many devices that can give you raw packets. But Kismet can detect advertising devices with just the Linux HCI drivers, so just standard Bluetooth and Linux. There's also a bunch of cheap USB devices that can capture Bluetooth packets, and you can get the BTLE advertisements and get actual raw packets that way. So you can see, nearby Bluetooth. So for example, there's a bunch of tile sensors. Those, I lost my keys, find it with my phone thing, along with people's phones, and it looks like either a Bose headset or a stereo or various things like that. So we can detect all of that at the same time as we're detecting Wi-Fi. There's also a protocol called Zigbee, which is a industrial control protocol for the most part. It's also used for some home automation stuff. With the right hardware, Kismet can capture that. You can get USB cards as cheap as $15 that can see that. Currently, the part of Kismet to display those packets as networks isn't available, but you can log it to PCAP and look at them in Wireshark. Some wireless keyboards can be sniffed and detected. Logitech, Microsoft, and whatnot use a chipset called the NRF or Nordic RF, where it's a little dedicated radio that isn't Bluetooth or anything like that. It's the keyboards that come with those little USB dongles that you have to plug in. Those can be sniffed. So if you have again a cheap USB device that has the right stuff, Kismet can detect keyboards that are near you. So given all this data we collect, we can detect different shenanigans going on near us. So IDS is intrusion detection system. WIDS was a wireless intrusion detection system because we're creative at naming things. So Kismet can detect attacks, it can detect denial of service, it can detect other weirdness going on. It doesn't attempt to prevent it. It's not a intrusion prevention system. Often that's not even possible. Someone can be messing with you and there's just nothing you can do about it, but knowing that it's happening is valuable. So Wi-Fi presents a very large attack surface. The packets are complex, the data in them is complex, they have weird nested cascading data structures that are easy to get wrong. Also, because anything transmitting near you affects you, it's really easy to cause a denial of service, either just by jamming the spectrum or by transmitting packets to say this channel's busy, this channel's busy, this channel's busy, and then the network never has a chance to do anything. It's also easy to do spoofing or impersonation, and there's been a number of attacks against various Wi-Fi drivers. So in the Kismet WIDS, there's three main types of alerts. There's trend-based alerts. So traffic that's otherwise normal, but taken over time indicates something is strange or broken. So like a denial of service attack that says, disconnect all the users from this network. That's totally normal to happen once, but if it happens 100 times in a minute, that's a denial of service attack, raise an alert. Kismet also has signature-based alerts where there's specific bad packets. Some of them are, buffer overflows in drivers or other malformed packets that are designed to cause problems. And those are easy to spot because those are never legitimate. So it's just, as soon as you see this, that's an alert. And also you can do user configured fingerprints where you can set up regular expressions and whatnot to match similar networks or to look for specific MAC addresses and whatnot, entering or leaving the area. So some example detections Kismet offers. One of the trend-based ones is encryption options changing on a known access point. So, we said devices are tracked over time. So the access point, we know what it used to advertise. We used to advertise WPA, and now all of a sudden, something claiming to be the same access point is advertising no encryption. That's almost certainly a problem. You could also write a regex to find network names similar to the official one. So if you have, the official one is called my network, and you can detect, my network underscore, someone trying to spoof to get people to connect to the wrong network at a conference. We can also detect brute force attempts against WEP and WPS and whatnot because they are fairly intrusive and transmit a lot of packets. So, the more data we have, the more discrepancies we can find in it. And we can look at other vendor-specific flags because often attackers don't completely duplicate a network properly. Also, just announced yesterday, there's a new attack against Bluetooth called Bleeding Tooth. And the Git version of Kismet now has detections for that. So if you have the Bluetooth BTLE sniffing hardware, you can detect that. I'm going to go through the last of this really quickly before Q&A. So get your questions ready. No tools island though. Kismet has APIs to talk to other tools. You can convert the log files for other tools. Old Kismet had a custom TCP protocol that nobody used. The new one just talks HTTP and JSON. Any language that can talk HTTP and JSON, Ruby, Python, JavaScript, Node.js, and whatnot can all talk to Kismet trivially. Everything has a REST-like API, and it's all heavily documented on the website. You can also stream PCAP over HTTP. You can also filter by device or access point or capture card live in the PCAP stream before you hand it off to another tool. And you can filter packets from the log file. You can also run Kismet through Nginx or another proxy. You can add SSL via Let's Encrypt. You can tunnel it over SSH. You can do remote cap over SSH, etc. The new logs are much easier to handle. Instead of multiple files, it's all combined into one with the packets, the reports, the device information, configuration info, alerts are all in one log now. You can convert those to PCAP or PCAP-NG, CSV, JSON, any language that can talk SQLite and JSON can do complex filtering and extraction of data from the logs. And now that the log is a database, it's random accessible. So we can do things like ask the Kismet server to give us all the packets that occurred 5 minutes before and after an alert. So now we can see, okay, this WIDS alert triggered, what happened? You can also extend Kismet with plugins. You can have native code. You can have external code written in Python or Ruby or whatnot that talks to it over IPC. Or you can have web-only plugins that define new interfaces. Here's a whole custom mobile web UI based on just a plugin that defines new HTML and JavaScript for the web UI. Coming up is going to be more WIDS features, WebSockets for simpler remote capture and a better UI interface, and handling packets from more types of data. And you can find Kismet at kismetwireless.net. That has links to the packages. Kismet has its own Discord. All the documentation is there. And Kismet Wireless on Twitter for release information. I'll post there when new releases come out or new features get added. And since there's no questions yet, here's just a quick example of, here's a Kismet server running with all sorts of different devices. We can filter by, here's all the no, of course we can't. The curse of the demo gods. In any case.
While you sacrifice a lamb to the demo gods, you do actually have 3 new questions.
Oh, here we go. So Robert asks, is there a tool that can take Kismet data and create a relational map to show what clients are connected? Not yet, but there is an API that gives you all of those relationships in a JSON record. And I started using one of the JavaScript-based graphing tools to do that in a browser, but it's not quite done. Isaac asks, who makes the 64 radio one? That's Alftel, ALFTEL. I believe they sell it as a handful of like you don't get all 64 at once, but it's a set of expansion boards that can be daisy chained. Kismet name came about because I was I think I put NetStumbler had just come out, and I think I put stumble into thesaurus.com and clicked at it randomly until I hit a word that wasn't another open source project that sounded cool. No great story there.
That is a great story.
Stefan asks, why isn't the same as on FlightAware? Because FlightAware is based off hundreds of people with antennas all looking for planes and combining them, whereas any given single antenna is not going to see all of them, either because they have better radios that are more discriminating and can see more packets, or because they're at a higher altitude or similar. That said, my antenna is inside my attic of my barn, and I can see planes that's about 300 miles away. So even fairly cheap gear, and mine's mounted indoors because I don't want to deal with lightning hitting it by mounting it on a big tower outside, can still see, a lot of planes far away. The problem with this is that it's easier to see planes that are 30,000 feet up, hundreds of miles away, than it is to see, helicopters and planes closer to you that might be below the range of a local hill or trees or whatnot. But if you had multiple sensors distributed around connected to one Kismet server, you'd be able to see more planes. As a test, a friend down in Philly has been running a server as well, and we've combined the two of them so that we can get coverage across this whole range, which is kind of fun to watch. David asks about WLAN Pi. I believe I've met them, but I'm not affiliated with them. So I'm not sure if they have plans to integrate it or not. I believe the guy who does that has been through the Discord channel a few times and we've chatted, so he might be working on adding support. And now things are cooperating. So here we can see, a bunch of different nearby devices. So, here's a weather station that's near me, so I can see, the wind direction and humidity, and that I need to replace the battery in it. And all that's coming off of one of those super cheap RTL SDRs. And then we have, Bluetooth devices that are near me. BTLE supports random MAC addresses. So there's often a lot of junk in here that sends, a few packets and then changes the randomization. But these are things like Nest smoke alarms. So you can, see things like that. Here's all the planes appearing off one of my sensors. And I mentioned how Kismet can do transparent remote capture. So of these, some of these are on my local server and some of them are remote. So, this is a USB device plugged into my local server, whereas this is a Raspberry Pi 3 in the attic doing remote capture of ADSB. So it's up high where it can see more planes. Robert asks, quick overview of WID setup. So by default, the alerts are all turned on. There's a page in the documentation that explains each of the alert types, but they show up here as alerts in this in the interface here. Unfortunately, I don't have any interesting ones here, but they'll show up in this, and then there's web-based APIs that you can use to pull alerts based on time and either of all time or recently. They're also logged into the log file, and there are some example plugins to take them and send them to syslog. There's also some optional code that can integrate it with Prelude monitoring engine, and then anything that can take syslog can be easily integrated in. Someone's asking, running on Mac OS. Yes, there's directions on the website. There is no package because of Apple's code signing requirements, but you just need to install Xcode and a couple of other utilities, and it will compile and build and run there the same as it does in Linux. There's a few quirks to compiling the latest release. I just replaced the entire core web server code to make it work better on Mac OS because the HTTP library I used stopped working on OS X correctly. But yeah, all the instructions are on the webpage. I can link it in Discord after the talk as well. Isaac asks, how does it merge the captures from different PCAPs? It works on fingerprinting the contents of the packet, so it will basically do a quick checksum of the non-variable parts of the packet. So it'll exclude the radio headers with the signal levels and just take the contents, either the beacon contents or the data contents, and do a quick checksum. And you can configure how many packets back that looks. I think by default, it keeps the last 2,000 packet hashes. So it just does a quick checksum and hashes back and looks for that and figures out if they are the same packet seen from multiple cards in the same time period. I don't know if there's any other questions.
So you already answered merging the captures from separate PCAPs. Got it.
Yep.
Yeah, I was just going to say, why don't you go ahead and show the link to the survey?
Yeah, I was trying to. It lost my mouse.
Understood.
So yeah, if everybody has time to fill out the speaker survey, that really helps. And I think we have a few more minutes for questions if anyone has any, or if I can show anything specific in the UI, happy to do that. And I'll be on the Discord after this for the if there's any questions people wanted to ask in that format instead. And if anybody wants to remind me of links I said I'd paste in that section, in that format, I'll paste them over into Discord.
So Jesse just asked if there was any recommended tutorials or education sources he could learn to integrate this into curriculum in the chat. So.
I mean, I'll make this presentation available. if you want to steal anything from it, by all means. There's also a lot of documentation on the Kismet site, both about how to configure, mostly about how to configure things and about the API. Just under the documentation link here. So depending what you want to do in a curriculum, it's certainly possible to just, there's also packages available for Raspberry Pi and whatnot, so you don't have to compile it. So if you install Kali or Raspbian on a Pi, like a Pi 4 or something, then you can just pull the latest versions or even the nightly builds onto it that way. But if you're also looking at doing, like, someone had asked, how does it integrate with for alerts? So for example, here's all the documentation on the API to return alerts. So this, has all the info about, the endpoints and what information comes back from them. And everything in here just comes from JSON. So everything presented in the UI comes from the REST API. So everything the UI does, you can automate or create your own interface for, or extract data for presentations or whatnot. And inside that API, it actually has, every single field has a name, a type, and a description. So you can query the server and get the raw JSON, or you can get the pretty format where it gives you all of that additional info, or you can directly query. So you can query the system to get a live listing of every field that's supported in the system. So if you're looking at the JSON and trying to integrate it with a tool, you can go in and go, okay, I have this weird field. What is that? So if it's it's a 8-bit integer, and that's what it is. So there's something like 600 fields, but each of them has a type and a description of what it is. So it's a lot easier to write tools to integrate with it. And I think that's about it for time. So unless there's any last minute questions, I will be in Discord. And thanks everyone for joining, and I hope you have a great SharkFest.
That was great, Mike. Thanks.
Thank you.
official.
Can you hear me okay? I can't hear you though. Oh, maybe I'm on. Hold on, my audio. It's my audio.
Oh, that's you. Okay. I was like, what?
My end. Yeah.
No?
Is that Sherry? I don't know where it's coming from. It's so loud. All right. I think so. Yeah, I think somebody's supposed to make me the host of this, I think. Is that Sherry?
We're pretty early.
There we go.
Your host officially.
Yep. I'm gonna wait a little bit though to
Yeah.
start it up, just because if we start it now, they're gonna have to look at us. Yep. How's your day going?
Well, I've been.
Oh, really? Nice. All right. Yeah, I had the mover just left. They packed up all of my stuff. All my stuff is gone mostly. I have way too much stuff left over. I don't know how that's gonna work. Yeah. Well, I technically have to be out of this house tomorrow. So yeah, when we're done here. Okay, good. I'm gonna go grab a water, and then I'll be right back, and then maybe we can go talk about this should be live stream on YouTube.
This is live stream, but it's also recorded.
All right. You want to just answer those questions in chat for me then?
Yeah.
I have the chat window up there. I'll try to keep an eye on it, but when my presentation's up, I don't think I can do that. So.
Okay. So if there is some question, well, I would not know exactly the question.
Yeah.
But you're still gonna be able to see the Q&A icon.
I don't know. Let's look, because when I'm sharing my screen. Yeah, I can see. Can't see the chat window. Oh, Q&A. There we go. I can have the Q&A. I can have the Q&A up while I'm doing my presentation. Yeah, it hides some of my screen, but I don't need to see most of my screen. I know. I can see that as well. Yeah, you can. If you see something that needs some attention, just give my attention. Interrupt me.
Okay.
You don't have to wait for any specific time. Just interrupt me. I can go with the flow on this pretty easily. So.
Okay.
Just an excuse me, Ross. There's a question.
Okay. So if you don't see a Q&A pop up, I should tell you. So.
Yep.
Perfect. Then we're
Although, can you see? What do you see on your screen right now?
I'm seeing your screen and then
Okay, but can you see the panelists? Can you see the panelists in the Q&A window? Oh, all right. So I can't have that up. Yeah, if there's a technical question, you'll just have to alert me, and I'll pull up the Q&A window.
Okay. I'll just. You want
Unless I get my second monitor up here. I have 4 minutes. obviously disturbing. Okay. Should we fire this off? Oh, now that's not right. There we go.
Okay.
All right. Did you hit broadcast ready?
I don't have the broadcast.
Oh, there we go. Okay. Now it's being broadcast. Screen share. Right, can you see the images? Can you see my face on the... Never mind. Okay. I can actually see you, Natalia, so...
Yeah, I see you too.
Okay. Hi, everybody. Welcome to SharkFest 2020 virtual. This is all new for me, actually. I prefer to be in person, talking to you all face to face. But this is the next best thing we've got. So I'm super excited about this. I sat in Sake's presentation yesterday, his 8-hour class yesterday about TLS. It was fantastic. My intention here with this class is to give you a down and dirty, simple approach to understanding what's happening with TLS encryption and decryption, effectively what every engineer should know about TLS. Now, the way I'm going to run this session is if you have questions, use the Q&A. Natalia will help me figure out which ones which questions need attention. I may have some questions for you where I ask you to raise your hand throughout the presentation. Otherwise, please feel free to ask questions. I really want you to walk away with this with an understanding of what's happening with TLS, especially if I can give you some visuals to help you get that understanding. So let's get started. So my name is Ross Bagurtis. My primary work is creating training videos for Pluralsight, as well as doing other types of training and other types of engineering consulting. You can find my work at pluralsight.com. Our goals for this session. First, I want to talk about the difference between SSL and TLS. All right, I want to explain what's one versus the other here. I want to then talk about encrypting data and the basics of encrypting data. I want to talk about the Diffie-Hellman key exchange, and I want to talk about it in a way of actually looking at the mathematics of how that works. We're going to look at the data encryption protocols we use to actually encrypt our data using HTTPS or using TLS in general. We're going to look at the TLS 1.2 and 1.3 handshakes. We're going to find out what TLS 1.3 brings to the table for us. And then last, we're actually going to do some work in Wireshark itself. We're going to take a look at some of those handshake messages, as well as learn how to capture the session key so we can decrypt our traffic in Wireshark. So let's get started. So first things first, I have a OneNote where you can, if you write this down and link to it, you can see my OneNote notes. And I'll bring that back up in just a sec. Actually, it's right here in my OneNote itself. I have a list of where you can find me on Twitter, my email address, my courses at Pluralsight. I have links for TLS Illustrated 1.2 and 1.3. These are really fantastic. That goes through and it annotates every component of every field of the TLS handshake. It's really impressive. It just takes a lot of time to go through these. And then I also have some captures that I'm going to use in my presentation here that you can link to as well. So I'll leave that up for a second. Actually, let's just copy that right into the chat window. Copy. And let's put it over here. All right. So web browser encryption. When we're talking about web browser encryption, of course, we're talking about using HTTPS. And there are really two major components happening there. The first one that we are going to talk about is negotiating the encryption session. The other one is encryption protocols used actually to encrypt our data between our client and our server and back again. So to negotiate that encrypted session, we're either going to use SSL or TLS. And I'm going to talk about the differences between those in just a second. Then we're also going to use encryption protocols. And these are the big ones that we're going to use here. There's actually a few more that are supporting cast members for these encryption protocols, but we're going to use one of these encryption protocols. The three on the left, RSA, Diffie-Hellman, and elliptical curve Diffie-Hellman ephemeral, ECDHE. Those are asymmetric encryption. The ones on the right, Triple Des, AES, and Cha-Cha-20, those are symmetric encryption protocols, which are actually going to do the bulk encryption of our data. So where did this all come from? And why SSL versus TLS? Well, back in '94, we have Netscape Navigator coming out. Now, Netscape Navigator was pretty revolutionary. I was in college when this came out, and it was pretty fantastic to have this real simple interface to navigate the World Wide Web at the time. It was brand new. It was mostly text-based, but it was still cool to have this. Businesses quickly caught on to the value of this web browser and HTML, transferring HTML documents using HTTP. So Netscape Navigator developed SSL. And SSL version 1 was never released. SSL version 2 was the first one. Very quickly, they discovered that there was a problem with SSL v2 and fixed the problem in 1995 to SSL v3. Now, something else happened in 1995. I'm sure if you were around then, you may have remembered getting the stack of floppy disks of like 30 floppy disks to install it on your computer. And that is Windows 95 came out with the famous Internet Explorer, right? And what happened after that, right? What happened right after this began is Microsoft started to really push that Internet Explorer was a function of the operating system, and the browser wars began, right? So here, shall we play a game? And Microsoft said, yes, we should. Well, what does that have to do with SSL and TLS? Well, by 1999, we needed an update to SSL, and Microsoft wanted nothing to do with the name SSL because Netscape gave SSL that name. So in order to accommodate Microsoft's desires, the name was changed. Now, SSL and TLS, these are all RFCs managed by the IETF. So this is all public information. So Microsoft played its hand. They were able to get the name changed to TLS. So instead of secure session or secure socket layer, now we have transport layer security. And even until recently, Wireshark, you had to type in SSL to do all of your querying, even though SSL was pretty much outdated back in the late 90s or the early 2000s. So TLS is the primary name now that we're using. we have TLS version 1.2 and TLS version 1.3. Now, does that mean that SSL is gone? No, the names are really interchangeable. SSL and TLS, it's the same thing. I've read some things online where it said SSL is only used for this one thing and TLS is only used for this other thing. That's generally false. They're the same protocol, just different versions of it. And if we're using anything less than TLS 1.2 at this point in time, we should really be upgrading to that. If you have a security audit done on your systems and they see anything less than 1.2 being used, they are definitely going to recommend that you change that protocol. So, data encryption basics here. We talk about data encryption. Typically, there's lots of ways to encrypt communication, but when we're talking about using TLS to encrypt the actual data, to encrypt the website information, to encrypt our credit card numbers, our usernames, passwords, things like that, what we're using here is a symmetric encryption protocol, right? So we're going to take our message and we're going to run it through an algorithm like AES or Cha-Cha-20, along with a unique session key. All right. And that key plus the algorithm is going to allow us to encrypt our message. Once the message is encrypted, now we can send it across a public channel where no one's going to be able to decrypt it, theoretically. Once it arrives on the server, we can then take the same algorithm that we use to encrypt it along with the same key and decrypt our message. Once our message is decrypted, now the server can respond to it if it's a GET request or whatever we're doing here. The challenge, though, is that we can't send our session key over the public internet, because that would mean anybody on the public internet could get access to the session key, which means that they could decrypt our data. So how do we resolve that? Well, this is where key exchange protocols come into play. So the key exchange protocols that we're going to use here, these are going to be used to actually generate a key that we can use for AES or Cha-Cha-20. Now, this part of the process is one of the more complicated parts. And it's often, when you look up information about how TLS works, it often focuses on this key exchange process instead of focusing on the big picture of what's happening with TLS. So you might hear somebody say something like, oh, I know how TLS works. The public key in the certificate encrypts the data, and then the server's private key decrypts the data. Well, one, we're not going to use RSA anymore, and because it has some issues with its implementation. And two, that's only part of the process. So what do we want to do here? I want to show you how the key exchange process works. Now I'm going to show you how Diffie-Hellman key exchange works. We're also going to look at the elliptical curve process as well. But I think the Diffie-Hellman process is pretty cool because the math isn't very complex. It's pretty simple math. So let's go through how this works. So in order to get the same key on both the client and the server, we're going to do some trickery with prime numbers. Now, included in the certificate that we're going to use through our TLS process, there are two numbers in there, a P value and a G value. These are prime numbers. These are going to be really big prime numbers. I've chosen two small prime numbers to make this easier. So we're going to send that certificate from the server to the client at some point during the TLS handshake. If we're using Diffie-Hellman for the key exchange, the client then is going to take the P and the G value and realize that that is the public key information. The client is going to have a private key selected that's going to sit in memory. And that private key then we're going to take and run it through a formula. And the formula is this. We're going to take the G value from our public key. We're going to raise it to the power of our private key. And then we're going to do this mod operation on it. And a mod is a modulus of P. Well, what is this modulus? Some of you, if you've studied mathematics, you'll likely very clearly know what this is. The rest of us may have to go back to third grade math to understand it. So let's do our third grade math lesson here. Whoop. So third grade math, 95 divided by 8, right? I put it under the little bracket here. This is, I'm old, so we do this the old school way of long division. And I come up with 11 point something, something, something. Well, I don't want to know the decimal values here. What I do want to know is what the remainder is. So in early mathematics, I remember we didn't care about the decimal points. We cared about the remainder. Well, the remainder is the modulus. So we're just looking for the remainder of a division problem here with our prime numbers, or with these numbers in our formula. So if I plug in the numbers here, 17 to the power of 8 mod 149, I get 5. All right, once I have that value, I send that over to the server. The server then stores that in memory, and it does this equation for itself. All right, so that 5 that we calculated, that is the encrypted key. It's not really the encrypted key, but it's a component that we're going to use to generate the key. Server is going to do the same exact calculation. All right, so server is going to run the G value of the public key, raise it to the power of the private key, mod P, and this time we get 16. So now the server sends its key, its encrypted key, over to the client, and now we're going to do the math that makes this all work. The math that makes this work here is we take the encrypted key that each device sent, we raise it to the power of the private key, mod P, from our public key. And when we do this, on the client side, we get 129. And on the server side, we get 129. Now 129 becomes our session key on both sides. All right, so the 129 value here, this is what's used now to do our bulk encryption with AES or Cha-Cha-20. All right, and notice that we've never sent the 129 across the wire. It's never been sent across the wire. And the only way to generate 129 is if the private key on the client side is 8 and the private key on the server side is 6. So unless we know the private keys of the server and the client, we're never going to be able to generate that number. Now, does that mean Diffie-Hellman isn't corruptible? No. It has to do with the way the random numbers are generated for both RSA and for Diffie-Hellman. We really don't want to be using Diffie-Hellman because of its implementation is the thing that's potentially corruptible here. It's the thing that we can attack is the implementation of these protocols. So this is Diffie-Hellman's operation. We use that to get our key, so then we can go do our symmetric key encryption using AES or Cha-Cha-20. If you notice, I'm not talking about triple DES, and we'll get to that in a second. So with TLS encryption, we have TLS version 1.2 or 1.3. Let's look at the differences that we can use here for the key exchange. For 1.2, I can use RSA, Rives-Shamir-Edelman. That's the public key encrypts, the private key decrypts. I can use Diffie-Hellman, and I can use elliptical curve Diffie-Hellman. Well, it's advised that we do not use RSA because the implementation has potential security flaws. It's advised that we don't use Diffie-Hellman that I just explained because of its implementation has potential security flaws, which means that we're left with elliptical curve Diffie-Hellman. So in TLS 1.2, we can negotiate this, all right? We can negotiate which key exchange we're going to use. In TLS 1.3, we don't have that option. We use elliptical curve Diffie-Hellman or we don't encrypt. So with TLS 1.3, we're using ECDHE. With 1.2, we should be using ECDHE for our key exchange. So where does that leave us here? Leaves us here talking about elliptical curve Diffie-Hellman. All right, so I have oversimplified this concept to a point of it being almost not real. But my goal here was to leave you guys with a visualization of what's happening with elliptical curve Diffie-Hellman, so that when you walk away and you're thinking about what's happening with TLS, you at least have this visualization to work off of without having to do any kind of hardcore math. So this is an elliptical curve. Elliptical curves can be represented by very specific algebraic formulas. Here we have different curve types that mathematicians have come up with and labeled. When we're using elliptical curve, the curve is going to be our public key. All right. And when we pick our public key, we draw a line through the curve, and that allows us to pick some points on the curve that give us some numerical values that we can use for our encryption. All right. So we take this curve with the line drawn through it. We're going to mathematically combine that with our private key, and that is going to result in the encrypted key. So remember from Diffie-Hellman, we ran it through the G to the power of A mod P. This is kind of the same thing here to generate that encrypted key. Then what we can do is we can take that curve with the line plus our encrypted key that we've calculated. We can send that over to the server. The server is going to repeat this process. It's going to take that curve, which is our public key, right? Combine it with its private key, come up with its own encrypted key. We're going to send that back to the client. And now we have all the components that we need in order to calculate a symmetric key. All right. So this is going to result in a symmetric key. So elliptical curve is more efficient. We can get a stronger key with less computation, and its implementation is less corruptible than with RSA or with Diffie-Hellman. So this is the key exchange that's happening. And it's a really important part of the process, but it's not the part of the process that's doing the encryption. This is just to generate the key. So we have the key exchange. Then we're going to go do the data encryption with the key that we've generated. We typically have 3 options here with some supporting roles for some other hash algorithms to validate our encryption. But we can use triple DES, we can use AES, or we can use Cha-Cha-20. Now, we don't use triple DES anymore. It's not recommended. We developed AES in the early 2000s explicitly to replace triple DES. So we don't want to use triple DES anymore either, which leaves us using AES or Cha-Cha-20. If we're using TLS 1.3, we can use either AES or Cha-Cha-20 in our encryption. So now we get to another component here, and that's handshake integrity. So in order to make sure that no one has corrupted, or in order to make sure that no one has interfered with our communication, like a man in the middle, we have some handshake integrity that we're implementing here to make sure that no one's touched our stuff, right? So what we do is we take little pieces of the handshake and we run it through a hash algorithm, and we put the result of that hash inside of one of the handshake messages. And that way, both the client and the server can validate to see if somebody tampered with the handshake message by checking the hash calculation in the end. We can use SHA-256, or SHA-384 to do this. It's recommended to use 256 or 384 bit values to do our handshake integrity. All right, so that's going to validate that no one has tampered with our data as it's traversed the wire and made some modifications to it. And so far, I've only talked about the certificate being used in this process once, really, right? And that's when we talked about Diffie-Hellman using the P and G values for Diffie-Hellman. So we still have this other component here, and that's server authenticity. We're going to use that certificate to validate that the server is who it says it is, right? So the server certificate can be used for RSA encryption. That's public key encrypts, private key decrypts. We're not using that. We can have the public key, the P and G values for Diffie-Hellman, but ideally we're not using Diffie-Hellman anymore, which means that really we're using the certificate to validate that the server is who it says it is through this certificate chain and signed certificates. So there's a whole lot to learn about certificates. We spent probably 2 or 3 hours on it in Sake's class yesterday, talking specifically about certificates. I'm going to spend almost no time talking about certificates here. It's an important topic, but more than anything, I wanted this session to be about engineers being able to understand what's happening with the encryption and to be able to decrypt their traffic effectively to do some troubleshooting or just for their own curiosity. So what's next here? Let's talk about our handshakes. All right. So TLS's handshake, we're going to look at 1.2 first, and then we're going to look at what 1.3 adds to this, or what it subtracts from this and makes it more efficient. So in TLS 1.2, the client sends a hello message. That's the browser saying, hey, server, these are the protocols I support. This is what I'd like to do. If it's using elliptical curve Diffie-Hellman, it'll send the curve type and the encrypted key. It'll send that right away in the client hello message. And it allows the server to figure out what it can negotiate then with the client. So then the server sends a hello message back and it says, okay, let's use these protocols to do our encryption, right? We're going to use elliptical curve Diffie-Hellman with AES 256 encryption and SHA-384, right? So the server will send back the cipher suite that it chooses. The server is then going to send its certificate. It's going to send the server's key if it's using Diffie-Hellman. And then the server is going to say, I'm done with the hello. The client then sends back a message saying, here's my key if we're using Diffie-Hellman. It's going to send the change cipher spec, which means that everything is set now. We're ready to start encrypting. And it says the handshake is finished now. I'm ready to encrypt. And it sends our handshake integrity information in that finish message. Server does the same thing, sends the change cipher spec, the handshake finish message. And now we're ready to use our encryption protocols to actually do our bulk encryption of data. This is where our usernames and passwords get encrypted. The website data gets encrypted, credit card information, all that gets encrypted now over the public wire. So in TLS 1.3, this changes. TLS 1.3 is a much more efficient protocol. What happens with TLS 1.3 is we send the client hello message. In this client hello message, we're going to negotiate the bulk encryption and handshake integrity protocols, but we're not going to be able to negotiate the key exchange, right? The key exchange is fixed. So it's fixed to Diffie-Hellman elliptical curve Diffie-Hellman. So when we send this client hello, right in the hello message is going to be the elliptical curve that was chosen plus the encrypted key, as well as the other cipher suites that the client supports. So the client key is sent right away with the client hello message. So the server can use this to its advantage. When the server sends the hello message, the server sends the server key as well. It also says, let's use this cipher suite. Let's use AES 256, SHA-384 for our encryption and handshake integrity. And now after this moment, the server and the client can start to send encrypted messages, which means that when the server sends its certificate over in TLS 1.3, the certificate is actually encrypted. So if you're man in the middling and spying on this, you don't have access to the certificate anymore. It's totally encrypted, as is the rest of our handshake message, which is basically going to be this handshake finish message. The client then sends a handshake finish, and now we're ready to start our bulk encryption of data. All right, so the TLS 1.3 handshake is much, much more efficient than the TLS 1.2 handshake. Do you guys have any questions so far? You can pop those into the Q&A or into the chat if you want as we go along. I'm happy to answer any questions you guys have. Or give me thumbs up if you think this is going all right, or thumbs down if you want to know information, or whatever's needed here. So yes, Nick raised his hand. You want to, oh, there you go. Can I talk about session tickets? I can only briefly talk about session tickets. in the sense that the session ticket can be used to resume a session. That's going to be a bit beyond the scope of this particular presentation. However, Peter Wu is the Wireshark expert on a lot of this. He actually writes the code for Wireshark's security, encryption, and decryption protocols. So, and he maintains all of that in there. So I would definitely ask Peter in his session. I think it's tomorrow or later this afternoon. I'm pretty sure it's tomorrow, though. Dimitri is asking, how does it know to use 1.2 or 1.3? All right, so we'll look at this in when we do the capture. In the client hello message, it will send a list of TLS protocols that it supports. So you can actually, the server will be able to determine what the client supports. The client may say, hey, I only support 1.3, and then the server will have to either talk on 1.3 or shut the session down. Or the client can say, I can talk on 1.2, 1.3, SSL version 3, or any other previous protocols, and then the server decides which one it uses. Dave is asking, how does 1.2 versus 1.3 impact TLS inspection for security devices? Right. So TLS 1.3 made it a little bit challenging for devices like a man-in-the-middle box that's explicitly used to inspect the traffic, like in a corporate firewall. And TLS 1.3 has included pieces of the 1.2 handshake in it, and it does some goofy trickery in the handshake to make it look like a TLS 1.2 message, even though it's TLS 1.3, and it leaves the function of that device unaffected. How is it possible that ECC has shorter key lengths than RSA or Diffie-Hellman and it's still secure? This is a question that is beyond my mathematical skill set. My answer to that generally is magic. And I think, though, if you find Peter or Sake, they may be able to answer that. They might be able to ask that in the Discord group and get that answered. Sorry, I can't answer that. And then what else do we have? Does TLS start at 1.1 and then work its way up to 1.3? No, this goes in the beginning. When we do the decryption here in a little bit, you'll be able to see there's going to be a list that the client sends, and it's going to say, I support TLS 1.1, 1.2, 1.3, and then it's up to the server to pick the right version. And then Craig over in chat is saying, if a client supports TLS 1.2 and 1.3 SSL, and server can support all of them, does the server choose the most secure? There are configuration settings on the server typically to choose the priority of which one you're going to use. Ideally, yes, it would choose 1.3 over anything less if it had that option. So, all right. Sorry, some of those questions were a bit beyond my scope, but I'm hopeful that you can find some other really awesome nerds here at SharkFest to help you answer those. So, all right, let's move on here. Oh, thank you for putting Peter Wu's session is tomorrow at what is that? 20 is 11 a.m. Pacific time tomorrow. So, all right, so let's go into Wireshark here, and take a look at some information.
I think there is another question in the Q&A.
All right, do I have to scroll down maybe? Let's see. Oh, there we go. Any tips on decrypting TLS SRTP? Yeah, let's see if this answers your question. If you can capture the session key, you can definitely do the decryption of any TLS transaction. I don't know the SRTP protocol. But if we're using TLS and we can capture the session key, we can do any of that. There's several ways to do that. I'm going to show you how to do it using Firefox and Chrome on both Mac and Windows. There are ways that there are utilities out there that we can get that will actually grab the session keys right from your memory and store it. There's other ways to do this with the man in the middle box. A lot of it is beyond the scope of this particular presentation. But let's see if what I'm about to show you will answer your question. So, all right. So let's start with Windows. Natalia, can you see my window screen up now? Does it say Pluralsight? Okay. All right. So if we want to capture our session keys using Windows, what we have to do is we have to create an environment variable. So what I can do here is just search in my window here for environment variable, edit system variables. And what I do is I go to environment variables, and I need to add this variable in the user variables called SSL key log file. So let me delete this and I'll re-add it so you can see exactly how to do that. You click new, all caps, you type SSL key log file, and then we browse for the file. And I'm just putting this in my documents folder, and I called it SSL keylog. I hit open and hit OK. You can call it anything you want. Does not have to be called SSL keylog.log. It can be called any question there, or any file there. Oops. The questions aren't scrolling automatically for me here, so. Okay, so this is for VoIP transactions. Okay, so yeah, unless your SIP client will dump the session keys, or you're using a man in the middle box that won't add too much latency to your calls. Then, thank you, Wes. Okay, so we add this SSL keylog variable into Windows. We hit OK. And now, I'm actually going to delete that SSL keylog file. And then I'm going to open up, and start up Wireshark, start a capture. I'm going to start up Chrome or Firefox. This will not work with Edge. It won't work with Edge. So I'll start up Firefox. And once I start up Firefox, we're going to see that the SSL keylog file gets generated. Just boom. Once it starts running, the SSL keylog file gets generated. Thanks, Firefox. Not right now. Let's go to https wireshark.org. And then we can close this browser. Close this one. And we can go over to Wireshark. And right now, all of our TLS conversations here are encrypted. And I can tell they're encrypted because, let's just do a TLS search here. I can tell they're encrypted because we see this information where it says application data. And if we open up the details of that, it's going to say it's HTTP over TLS, and then it gives us this encrypted application data. So in order to decrypt this, we just have to grab that session key and apply and insert it into Wireshark. So to do that, I'm going to go to I'm going to right click on anything that says TLS in here. I'm going to right click on it, go to protocol preferences and open TLS preferences. I'm going to browse for the keylog file, select it, hit open, hit OK. And now it didn't decrypt it. There we go. Actually, it did decrypt it. Here's some decrypted messages. Oh, it just took a second. So suddenly now, instead of having application data, now the encrypted application data still shows up in our detail, but then it also shows us our HTTP data. And now we can start to use that to actually see exactly what's happening here in our conversations. All right, so if I try to find my wireshark.org one here, let's do frame contains Wireshark. That'll show me here's my TLS hello. Let's do a follow TCP stream on there. Or as Jasper likes to do, conversation filter of TCP. And now we can see this conversation. It's using TLS 1.3 to do this. So let's take a look at this handshake quickly. All right, TLS 1.3, we send the client hello message, right? We have SYN, SYN-ACK, ACK, and then the client sends the hello message. So this is Firefox sending the client hello message. Let's take a look what's inside of there. So inside of the client hello, we have some general information. Then we have the cipher suites that are supported. All right. The ones that are TLS 1.3 are going to be the first ones. And there's only 3 of them here. So the first 3 here are TLS using AES 128, SHA-256, SHA-20, SHA-256, or AES 256, SHA-384. So those are our 3 options for TLS 1.3. How do I know those are the 3? Well, those 3 do not have a key exchange protocol listed, right? Because in 1.3, we already know what the key exchange protocol is. However, we can tell that this client also supports protocols besides TLS 1.3 because it has all of these options here. We can use elliptical curve Diffie-Hellman, or we even have RSA options, all right? And the reason that we have these RSA options that we can actually configure TLS 1.2 on the server side to use RSA, and then we don't have to worry about capturing our session keys. We can go grab the private key from the server, put that into Wireshark to do our decryption. So a lot of engineers like to do testing with this, but it's not recommended that we do this with production equipment. Natalia, can you just read that question so I don't have to swipe between my OSs here?
Manfred says, you may check also the commercial solution using a tiny sensor agent, which captures the TLS session keys from clients or server's memory and transfers it.
Yes.
Also encrypted.
100%. Yes. Yes, absolutely. Yes. That's exactly the solution that you'd most likely want for that, for the voice over IP conversations. 100%. Yes. Yeah. Last year, one of the sponsors was the company that does this, and the name is escaping me right now. So if somebody can remember that name and type it into the chat, I would be grateful.
I think he wrote it down.
Nubeva, yes.
Okay.
That's one of them. There's another one out there too. Okay, so going on with this. So we have, no, not ProfiTap. That's a different one. They may be able to do that, but this one is it's a client that actually gets installed right on your device, and it goes and grabs your keys out of memory. All right, let's move on with this. So right away, we can tell, since this client is supporting all these options using where we can choose the version, where we can choose the key exchange protocol. We can tell that this is going to support more than just 1.3. So if you go down here, we can see our key share information. If we look at the key share information, here is where we're sharing our elliptical curve key plus the curve and the points on the curve. So this is our public key plus our encrypted key information that we can use to do ECDHE key exchange. And by default, our Firefox client automatically chooses to send 2 separate keys. So it gives the server an option to use either X25519 curve or SECP256R1. So the server then can pick which one it wants to use if it's going to use Diffie-Hellman or elliptical curve Diffie-Hellman. All right. So this is sent right in the hello message. So if we end up choosing TLS 1.3, the server already has the key information from the client. Supported versions. All right. There's a couple questions about this. Here is Firefox telling the server which TLS versions it supports. Now, the current version of Firefox only supports 1.2 and 1.3. However, you can go into some expert configuration spots in Firefox and actually turn on older protocols if you choose to do that. All right, but by default right now, TLS is only supporting, Firefox is only supporting TLS 1.2 and 1.3. The rest of this, although it's important, I'm going to leave that to you guys to go investigate that a little bit more. Let's go take a look at what the server said now. So the server came back and said, all right, sounds good, client. We're going to pick version 1.2, or are we? Well, version 1.2 here isn't real. All right, this isn't actually using version 1.2. How do I know this? How would you know this? Well, look at the cipher suite that was chosen here. We can tell right away from the cipher suite that was chosen that this is not TLS 1.2. And how do I know that? There is no key exchange protocol listed here, right? We're only listing our bulk encryption and handshake integrity protocols. So, so we know that TLS 1.3 is in operation. TLS 1.2 is being stated here for those man-in-the-middle boxes, for those security devices that that are decrypting and inspecting our traffic, right? So those corporate firewalls that are inspecting the traffic, looking for nefarious information and some data loss prevention. This is set to 1.2 for that exact reason. So RSA here is, so the RS for this question from this question that popped up in chat here, is there any other algorithm than RSA to authenticate the server via certificate? Are there plans to replace RSA in the future? So as far as I understand, using RSA to generate the certificates is acceptable. Using RSA to generate the certificates, validate the certificates, this is all acceptable. The challenge comes in when we're using RSA to do the actual encryption to generate our key, right? When we're using RSA to generate the key, that's where the problem comes in. I don't believe that RSA is problematic to generate the certificates, at least not entirely yet. All right, and then thank you. Manfred says TLS 1.3 cipher suites all use the same hex number string starting with 1.3. And you can see that right here, 1301. Right. Thank you. All right. And moving on here. So we can see then that the server is sending its key share information back to the client. All right. So the server is saying, okay, great. We're going to use X25519. Here's my key information. right? And now after this, everything is going to be encrypted after this. Now, it's not going to look like it's encrypted here because I've already put in the session key, but everything in our handshake after this is going to be encrypted, including our certificate, right? So here the server is now sending the certificate information to the client and saying, yep, we're all done now. Then the client comes back and says, we're all done. And now everything after this is encrypted. All right. So here we can see HTTP kicking in and transferring our website. We can see all of the HTTP information, TCP information. None of this is encrypted now because we put in that session key. All right, let's go take a look at how to do this in Mac. And then we will we'll look at how to do this on the Mac. We'll look at a TLS 1.2 handshake and see how it's a little bit different. And then I'll answer some questions and we can start to wrap up the presentation. So here I am back on my Mac. Now, in order to get the session keys on a Mac, we have to launch Firefox from a command line. So we're going to use the command here. We type in export SSL key log file equal to, and then we give it a location. So I'm going to do this the easy way here. And just drag this right over here. There we go. Next, I want to start Firefox. Open -A, and then I go over here and find Firefox and hit enter. That should launch Firefox for us. Let me start up Wireshark. Start a capture. Thank you, Stefan. Oh, I forgot the same thing here. Can you see, you guys can see my face, I'm guessing? Yeah. I forgot to put this on. Oh, and you can't even see it with my virtual background. Look at that. Rawr. Oh, it's just too hot to have that on right now. So, all right. Let's start up a capture. Oh, I did start a capture. Oh, and that was the wrong interface that I started on. All right. I think this is it here. I have to find my interface. Just a moment.
There are two new questions. Dave asks if it doesn't work with Chrome on Mac, or is it only Firefox? Yeah, it's the same question.
It'll work with Chrome on Mac. Yeah, Firefox and Chrome both work. I don't think Safari works, but I have not tried it. We can test that here in just a minute. So USB. There it is. All right. So let's go to https wireshark.org. There we go. Let's close this. Stop our capture, which is a disaster because of the Zoom, all the Zoom messages. Let's go find it. Wireshark, or frame contains Wireshark. There we go. Conversation filter, TCP. All right, so let's take a look at this. So is this session encrypted? It appears so, right? Because we're not seeing any HTTP data. We can look on our sidebar here and see that it's all purple. And there's no green in there. If there's some green in there, that would mean that it would be decrypted. Marcus is asking if it would work with Firefox or Chrome on Linux, and the answer is yes. This should work the same exact way on Linux. All right. So let's decrypt this traffic. Let's go put our session key in here. Remember, we click anywhere on transport layer security, open our preferences. Let's go grab our session key from my documents folder. Hit open. It'll take a second to process that. And there we go. Session is decrypted. All right, let's take a look at our TLS 1.2. Oh, this is TLS 1.3 again, because I captured the same website, of course. But we can go grab a 1.2 as well. So this is how we get our session keys in on a Mac or on Linux. Let's test this with Safari quick to see if it works. I'm going to go delete my session key. I'm going to delete that file.
Somebody is asking, sorry, Ross.
Oh, no, you're good.
Somebody's asking if it maybe work also with the new Windows Edge, which is now running Chromium in the background.
Yes, we just did this test yesterday in Sake's class, and the answer was a definite no. It does not work. It doesn't. When I delete the SSL keylog file like this, and I opened up Edge, it did not populate the keylog file. Let's see if it works with Safari here. I don't think this is going to work. Oh, where'd it go? No, so Safari, well, let's go to a website. No, so Safari is not generating this either. And it does not work in Edge either. In fact, I can show you. It's easy enough to just show you guys that it doesn't work. And there may be another way to get that file, but I don't know how it is using Edge. So there we go. I deleted that file. If I open up Microsoft Edge, it should have already populated that keylog file by this point. So yeah, it doesn't populate the file. If I launch Firefox or Chrome, it instantaneously populates it. Right there it is already. So it doesn't work on Edge, doesn't work on Safari. You'd have to use a different solution to get there. All right, let's take a look at a 1.2 conversation, and then I'll see if there's any other questions remaining, and we can start wrapping this up. So in that link I sent you, or the link in my OneNote, there's all kinds of examples here of different encryption protocols. Let's do one with Diffie-Hellman ephemeral. Let's make sure I have that keylog file. Now we'll have to do this one. So this is a capture I did from pluralsight.com. It's using TLS 1.2. If we take a look at that client hello message, take a look at the client hello message, we're going to see that. Let's look at our supported protocols here. Well, we'll just start off with, did I select the client? Okay, there's the client hello. Cipher suites, here we go. This is what I was looking for. It's right in front of my nose. So our Cipher suites this time, are we going to be using, or do we have an option to use 1.3 in this case? You can, Jorg is saying maybe an only slightly outdated link on how to capture the Wireshark. Okay, so maybe that'll go through. Oh, okay, I see. There's a question above that. My bad. What was the command string you used to put into the terminal? It was export SSL keylog file. Let's just type that in here. There we go. Okay. Let's make this bigger again. Okay. So here, are we going to, do we even have an option here of using TLS 1.3? And the answer is likely no. How do we know this? Well, one, the hex values for our protocols, just as like somebody pointed out earlier, none of these have a 1.3 in front of them. And two, if we just look at the name of it, none of them have, or all of them have a key exchange protocol listed here. So we're only going to have an option to use at least TLS 1.2, likely not TLS 1.3. Looks like I have some questions coming in. I'll get to those in just a second here. Supported groups. Here's for our elliptical curve supported groups. So here with TLS 1.2, we don't need to ask the server which version we're going to use. It's going to use whatever it can use, right? Server comes back with its hello message. This time the server hello says, okay, we're going to use TLS 1.2. We're going to use elliptical curve, Diffie-Hellman ephemeral with AES 128 and SHA-256 here. Right, so we're going to be using the elliptical curve. It gives us the point format that we're going to use here as well. The server then sends its certificate, the key exchange information. The client then sends its certificate, key exchange information, and says, okay, I'm all done. The server says, okay, I'm all done. And then we have our application data, which is our encrypted data. Safari and iOS does not have this feature natively, no. What are you going to use to grab the session token? I don't understand the question. So session keys, you don't have to provide the private key to decrypt. No, it's literally the key that's being used to decrypt it. Right? The only time we're going to use that private key is with RSA encryption. So this is Jeff's question. So session keys, you don't have to provide the private key. No, you do not. That is just for RSA encryption using Wireshark. Is it just Wireshark? I don't know. Roger, if you can be more clear on your question, I'll see if I can answer it. I guess Rick is asking, I guess a firewall that does not deep packet inspection by doing this man in the middle is pretty much not doable since the cert is now presented after the encryption started. No, because that device is the man in the middle. It's terminating those firewall devices terminate the SSL connection, right? So Instead of having client, my client here, my desktop that I'm using to do the captures, instead of that having a full connection all the way to wireshark.org and back again, that's not actually happening. The client is negotiating its SSL session between the client and the man in the middle box, the firewall box, and then the firewall box is doing another session between the firewall box and wireshark.org. So in the middle there, it's actually unencrypted at that point in time. So we get the session keys because the box in the middle has the session keys. It's generating them for both the client side and the server side communication. All right. Hopefully that makes sense, Rick. Can you confirm that TLS 1.3 has to be in an extension supported version? Otherwise, it's not available during the handshake. I believe it has to be in that it's extension or it will not be supported because, that the client hello, if we just compare the client hellos here, this client hello is missing information that's required to do elliptical curve Diffie-Hellman. And hopefully I don't put my foot in my mouth here, but there is no key exchange sent here. There's no elliptical curve key exchange sent in this hello message when it's only using 1.2. So it has to, that extension does have to be there in order to get this to work correctly. You mentioned that with TLS 1.2, you could get the key from the server. Where do you get that? With TLS 1.2, you can get the key from the server if you are using RSA to do your key exchange. Only if you're using RSA to do your key exchange, which we don't advise doing in a non-prod environment. Is there any similar technique to decrypt SSH sessions and look into the date transmitted in the SSH tunnel? I do not know. I personally don't know how to do that. Some interesting information on iOS for decrypting using TLS session keys. All right, great. Thank you for posting that. All right, and Gabriel saying, I tested after Sake's class yesterday and it works in the new Edge. I assume whoever tested it was using an older version. I just did it with version 86 and the session keys are logged. Okay, excellent. Maybe I do have an older version of Chrome or of Edge. Let's take a look. I've literally never used this program. Not ever once. Is there an about here? Go away. Like I don't know what's happening. Yeah, no, just stop. All right. Yeah, I don't know. I don't know where the about is. That's fine. Okay, it's definitely an old Edge. All right, so everybody is confirming that it does work with the new Edge. I just didn't have mine updated, so thank you for that. Is there a site to walk you through the Windows SSL keylog setup? This session is being recorded. It will be available on YouTube. I go through the same process in last year's session 2 for SharkFest 19 in the US. So you can go back and watch that as well. Ross, I think you're using the old Edge. Yeah, I agree. I agree, Manfred. I'm very likely using the old version of Edge on there. Settings help. Thank you. Got it. Thank you. Clippy, new Clippy. Did I type that wrong? Well, it did a Bing search for me, which is exactly what I wanted. All right. Well, thank you guys for the help on that. It's probably for the newer version of Edge. You're right on. Thanks for the help on that. You guys, if we were doing this in person, we could all go have a beer after this and you could razz me on my inability to use that browser. So, all right. Do we have any other questions that I can answer? I really hope you guys found this useful. I realized that this wasn't a deep dive, wasn't intended to be a deep dive. This was supposed to be an opportunity for everybody to get a visual idea of what's happening with TLS so that you can use this information to actually do your work better and have a better understanding and not have to go online and listen to somebody tell you that in TLS, the public key encrypts the data and the private key decrypts it, because that doesn't help you at all. So, all right, we have 5 minutes left here. So if there's no other questions, if there's a last minute question you have, fire away. I really hope you enjoyed it. Here, let me put the feedback thing up here so you can leave me some messages and tell me how great or how awful I did. So you can scan that on your phone. I would wear the shark hat for the entire presentation, everybody, but man, this thing is hot. It's so hot, and it's about like 75 or 80 degrees and super humid here right now. So I'll leave you with da 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 da. All right. Good luck, everybody. I know you're all around the world. I know this was some of you had to wake up super early or stay up super late for this. I'm so grateful for everybody attending. Yes, Dent, that information was right at the beginning of the chat. Right in the beginning of the chat, there was the link to my OneNote. Let's see if I can put it in here again quickly before the session ends. I'm glad you all enjoyed it. Thanks, everybody. All right. How do I end this? I just leave? All right. Bye.
should use a background, because if you don't use a background, then you get to see the bird on my shoulder.
Oh, that's adorable.
My wife is saying no bird on my shoulder while I present this time, because
You're welcome. You're welcome.
it's bird's bedtime, and bird will start to be really loud. Okay, so this is the it looks, at least what I can see looks fine. Does it look good to you guys? Okay.
So I shared Discord, as soon as we start broadcasting.
Yeah, because it's not, if you put it on the chat, then they come on, they still don't see it. So once we start doing the thing, so about halfway down through the session, we'll start with working the packet traces.
Perfect.
So I'm gonna fire up. I'm just gonna be sharing my desktop.
Sure.
And so I just want to make sure that so you seeing my slides now?
Yeah.
Yep. And then you're seeing the card. Okay. Yeah. Then we're good. So I'll just leave it right there.
For the questions, you want to wait until the end, and unless it's you're unclear on something, correct?
Yeah. So well, actually during the packet trace analysis, I think we'll have we'll so questions during then will be good. And if you can just prompt me to make sure that I have, I'm gonna need another 8 minutes to finish off the last 10 slides.
Okay.
So that would be good to keep me from just running on and using up all the time.
Okay.
Although I guess it's not so bad because we have that dedicated 15 minutes of QA time.
Yeah.
I guess if we go into that because we do Q&A during, I don't think
Yeah.
All
So I
the
think
wasted
it's
battles
important,
under your heavy belt.
yeah, and then that'll give time
All-nighters
to
at
get
sweet,
back on
sweet
track.
lies, turning into landmines with your golden touch. There's not much
I see
room
the
for
Q&A,
love.
and
I heard the whisper, do the crash and know the reeds are dancing. You whistle out a tune.
while I'm presenting, I don't think I do, but I think when I stop sharing, then I can see the questions. I can bring it up.
So if there's
Yeah, so for most, I imagine most of them are going to be people asking for details, and those will wait till the end, and pretty much I'm not going to be able to share too much detail. People are going to ask, what product do you use? Do you have an infrastructure? Where do you put your tap? All of that stuff we're not sharing. So and we're sharing some of the results here. So I don't want to get bogged down in discussion.
But even gold can
I
melt into
will, when I get to the end, then we can go on about all sorts of theoreticals. But
mighty
I
ears.
don't. But if someone is questioning, how do you see this? If there's something about the process that they're asking, then please break in and ask that question.
so you want to do
So we're just going to see my So I've got a somewhere in there.
There you go. Yeah.
I was doing another one so that so for the last 2 weeks that at work I've been doing this one advertising. So we got 15 or so people here attending. So they all knew they were attending. They all signed up long before I started advertising.
So the cherry document
Okay, I'm good.
You're good? Okay.
Yep.
Everything is so unclear. Street lights are dancing, shifting their glow. Oak trees are humming, soft and low. Stars are goldfish swimming through the night,
But she said
and your voice is coming through. Memories clenching, the teeth in the dark. Old habits, they die hard. I'm drinking your name like sap down my throat. But when I swallow, it's dry. I've tried so hard to let it go that I almost forgot to hold it close. I've tried so hard to bring the morning sun. Shadows are melting like dewdrops, they glittery. I've tried so hard to let the darkness go. Night is resting as I hold your hand. Moonflowers blooming, their hearts expand. Our city, it's floating, stretched beneath our feet. And your smile is coming through. I've tried so hard to let it go that I almost forgot to hold it close. I've tried so hard to bring the morning sun. Shadows are melting like dewdrops, they glittery. I've tried so hard to let the darkness go. I've tried so hard to let it go that I almost forgot to hold it close. I've tried so hard to bring the morning sun. I've tried so hard to let it go that I almost forgot to hold it close. I've tried so hard to bring the morning sun. All I remember is a shiver slipping down my spine. Your mouth pressed coming gently to mine. And the waves beneath us crashed, breaking on the towering stones, splitting rays of sun on the shore. The breeze was spilling memories. We laughed, salt sticking to our clothes. The water felt so sweet with the sand between our toes, erasing everything we used to know.
So just looking at the clock, I'm seeing it at 6:41. I'm on the East Coast. I know for all of you, it's been a long day, a big day. My first conference since that whole COVID thing started.
Memories talk, memories walk, memories true, memories false, memories washed away. It's okay to let them hold you,
Very
hold
nice
you.
in this virtual world too.
Memories know, memories show all of the scratches on your soul. It's the debris that weighs you down.
I'm seeing so the halo thing, is that a problem?
Bottled in a capsule, melted romance in a jar.
Yeah, we can turn off the virtual background. You can look at
When you
my
think that
house
you
if you
have it,
Does that
turns
help?
out you
I
went
cleaned up a
too
little bit,
far.
but still a bit of a mess.
What I don't remember
You see my bird,
is what I
who
want
was just
to
on my shoulder a few
forget.
minutes ago, but it's past birdie bedtime.
We were young, speaking
Normally
tongues.
sits on my shoulder
Thought we
for
could slide
8-10 hours
side doors unnoticed.
When it gets dark outside, she wants
Words
to go.
have consequences. They'll catch up with you.
How about this
All
one?
those.
So you can go for a ride with me in my my Miata. Oh, I guess it's nearing time. I should probably stop playing. Hello. So I don't know if we want to start right away. I'm not sure if we have if we've reached a quorum, but I think we can get going. My name's Chris Hall. I work at Capital One. I'm a distinguished engineer at Capital One. We've got a network team. I'm inside the network analysis portion of that team. We've got a bunch of different engineering sections there. We actually support operations and we support engineering pieces. I've been at Capital One for 5 years now, but I've been doing network analysis for quite a while, and performance analysis looking at more than just the network before that. So I spent 8 years at SWIFT, the Society for Worldwide Interbank Financial Telecommunications, went to Fidelity, Mill3 OpNet, where I was actually doing some developing for a while, went to Hitachi for a little bit, and then went back to OpNet. Then they were bought by Riverbed, but I've been with Capital One now for 5 years. Really, everything related to network and performance analysis has been on my plate. I was just trying to remember, because I heard some other people in the presentations. I started working with sniffers back in 1988. In 1997, we built a lab, and I reverse engineered the Novell protocol suite by looking at their packet traces and then building a model of that for OpNet Modeler. I don't think anyone ever used that model, but it was an interesting experience. And then I've been working with Ethereal and then Wireshark as it evolved since then. And despite my years of working with OpNet in their ACE transaction analyzer product, I spend a huge amount of time in Wireshark, and that's really my go-to tool. And so I'm going to share some of the stuff that I do in terms of network visibility, particularly related to particularly related to the cloud. Somehow, okay, so it looks like I got this going again. So Capital One has been working on going to the cloud for quite a while, and we had some stuff in 2013 where we were trying stuff out with private clouds. In 2015, we announced a strategy to go to move all our computing environment into the cloud, and actually it was as a AWS first strategy, so they're our primary provider. And this year we shut down the last of our data centers. We still have what we call regional hubs, COs. These are network POPs. So that's now where we have a lot of our visibility resources, and we keep them there, for a bunch of different reasons. But that's how we interconnect. As we move to the cloud, we have put into place a lot of very state-of-the-art modern technologies. You name it: big data, microservices, serverless streaming data, and so forth. And together with those technologies, we've put in place a lot of modern processes. We're an agile shop. We reuse a lot of code. We use APIs. We are big into open source as well. So, fits in well that we're working with Wireshark, although I don't think we've contributed anything yet to Wireshark, but maybe we will. We contribute to a lot of other open source projects. So as we're going to the cloud, one of the things that you first have to ask is, what do we have out of the box? What kind of out of the box visibility for the network especially is available? And you can get some interface monitoring. Okay, I got an EC2 instance. How much traffic, how many packets, how many bytes go through that? Okay, I've got a pipe leading into there. How, what volumes do they have there? I can get some up-down stuff. Like if I lose a load balancer, I should be able to see that. If I lose, one of my databases, hopefully it's fully resilient, and I, even when one instance goes down and I see that, there's plenty of other things there to take up the slack so that it's fully available. But I can't see the network. I don't have an idea about the switches, the routers. It's nothing that, as a customer of the cloud environment, of AWS, of GCP, of Azure, that we ever really see. So we can't see the up down status. And sometimes we can get some ideas. There's a lot of log-based information as well that goes beyond just the interfaces. So we get some flow stuff. There's access logs. A lot of the different services have their own monitoring capabilities that we can take advantage of. But when we're looking at the networking, how does the cloud fit into our monitoring strategy? When we had our own data center, we had a very full suite of network monitoring tools. But now that we're in the cloud, we don't have, we don't own the network components. Some of the pieces that connect to it, yes, but the components inside of there, no, we don't own them, and we don't have direct polling. I can't say, hey, Mr. First Hop router, are you up? And are you dropping any packets, please? And what's your CPU utilization? How's your memory stat? That kind of thing that we could do with our in-house network in our data center and for a wide area network, we can't do for those cloud components. So we're looking at how to expand so that we have the visibility and the correlation to be able to understand what is going on and when we have issues in the network to be able to give us the level of service that we need now that we have all of our stuff in the cloud. So I'm just going to go over a little bit about what it means to be in the cloud, and I'm not going to be sharing a lot of real details as far as how we do everything. I'm summarizing a lot of stuff. Hopefully you can understand in this cyber aware environment that we don't want to give you a lot of details, but I want to share with you enough so that you can see the levels of complexity and the challenges that we're facing. So first off, we're building a resilient environment in the cloud, and that means a resilient network to connect to it, and that the cloud itself should be resilient. So there's multiple AWS regions that we're going to. And we have our regional hubs. We have multiple of those AWS regional hubs, and they interconnect. Direct Connect is the basic building block to go into AWS, but there's similar connectivity that we have also for GCP and for Azure. So high-speed links that connect up our networking environment with the cloud providers environment, and these are done through those regional hubs, and fully resilient so that we can withstand multiple failure scenarios that you might envision. And so this is just a I think, yeah, sorry, it's for some reason it's skipping a slide. I have to hit it twice and it goes 2 slides. So inside, in this case, AWS, we're looking at, we have the multiple regions, and the providers, AWS, GCP, Azure, and by the way, we're looking at mostly a IaaS and a PaaS, platform as a service and infrastructure as a service. That's what these Azure, GCP, and AWS are providing. Similar concepts for SaaS, software as a service, but you're one level removed from there. But when we're building out inside AWS, we have multiple VPCs. The VPCs belong to an account. Those accounts have VPCs in multiple regions, and inside each of those regions, they split this up into availability zones. The availability zones are essentially data centers inside a region. So for instance, AWS has a US East 1 region, which is in Virginia, and they have multiple availability zones. I think they have something like 5 or 6 availability zones there, which are essentially data centers inside of that. And then when we're building out, then that's where we put our application. We distribute them for different business units and the applications that run on top of that. We put those inside the accounts and the VPCs, making use of those different availability zones. So you can see the network connectivity to pull all this together is quite it would be quite convoluted, and it's hidden from us. So when we connect up our VPC to our Direct Connect link, for instance, and it transparently handles all of the routing, and that at least that's the intention. Uh, so here's just a real simple concept. This is this is not how it really looks, but we have our stuff shown on top, the gray bits, Capital One sites, what have you, connected in through these multiple regional hubs, and then we have a connection into the AWS environment, to the different VPCs. And note that the internet connects into AWS directly. It also could connect into the regional hubs, depending upon the use cases. And sometimes AWS can talk to the different regions amongst themselves, so they can have their own conversations, or they can do that through regional hubs. There's a whole sorts of different ways that you could conceivably connect this. So let's see what this looks like. So if I have traffic that's going from one of our Capital One sites into AWS, then it's possibly going to be transiting that regional hub. So you can see that we have some opportunities for how we can get visibility to the network traffic. But there's more than one visibility solution there. But that gives us some unique opportunities. So if we have visibility to the traffic, at least going into there, and we'll talk a little bit later about how we expand from that, let's take advantage of a packet broker environment where we can get data, the packet data, feeding into DPI probes. And what I'm calling a DPI probe. So this is not, I'm not doing a sales pitch here. I'm not talking about any particular products, but if you have so what does DPI mean? Deep packet inspection. In fact, how deep do we need to go? Really, we need to go to layer 4. So I'm not talking about TLS and trying to look at the contents of the data. What I need to do is I need to be able to see the TCP level, the TCP level semantics. So in addition to the volumes, how much traffic, how many bits, how many bytes, how many packets, how many new connections, and maybe even making sense of transactions there, I can see the response size, I can see a request and a response. But because I'm looking at TCP, the TCP semantics, I can see things like retransmissions and packet failures. Sending a sequence of packets, and one of those packets is not there, I can detect that. I can then see it later retransmitted. I can see duplicate acts, all these different things that we do by looking in Wireshark at packet traces can be done in real time by a DPI probe. And how do we make sense of it? We need to aggregate it by account, by VPC, by the availability zone, by the application. However, we need to slice it and dice it so that we can make sense of that. And I put, certainly by the IP address, by the port, which may map to an application, but an application is probably, makes use of a lot of different things there. So the big thing here, we're looking at layer 4 to get some idea of what's happening. And when we do that, then do we get some idea of what's happening inside AWS, even by just sitting and watching the traffic in and out of there. And the answer that's come to us is yes, we are getting some good data. So here, let's look at all our traffic that's going in from a regional hub into into AWS or into a specific VPC, and we can see things like retransmission. So there's something going on there, and we can break it down and see which particular VPC. So these are and this may map to an account or inside the VPC to specific availability zones. So we now can see, although we don't know the exact path that it's taking once it goes into the cloud, we can see the impacted pieces inside of there. And that thing about correlation, now we can make a lot of sense of that. We can do that correlation and figure out what's going on inside AWS. So not only by monitoring one particular application or many simultaneously, but I may also know something else. Well, that VPC, I know, even though I don't have visibility to 5 other applications that are inside that VPC, maybe I have some good idea of what else might be impacted, even if I don't see it. So, yeah, first thing you're saying, well, of course, it's the cloud. There's never going to be any problems because AWS builds everything perfectly. Well, it's not always the case, because obviously, if it was the case, you wouldn't be here. I wouldn't be here talking about that. So we need to take a look at that. So to do this TCP monitoring, realize it's the end-to-end semantics. So it's not, it's not looking at a packet going through a router, but I have the IP address. So for instance, if there's a client talking to an application via load balancer, if that load balancer terminates the TCP connection, then if there's a problem anywhere along that path, whether it's in my, the network close to the client, maybe it's his Wi-Fi connection, or maybe it's in, maybe there's some MPLS or VPN or something, or maybe it's, in one of these high-speed direct connects, there's multi-gig links in there, or even inside AWS's own SDN. This is the piece that we don't have visibility to. In fact, we sort of don't have visibility to some of these other things. I'm just showing these conceptually, not trying to give you the full details of everything, but if somewhere inside of there, we start to have problems, whatever those might be, then even though we might be monitoring someplace else, if it's inside this monitoring domain of the TCP connection, even capturing on the client, I can see if there's a problem in the SDN in that part right there just before the load balancer, or even in the load balancer itself, I can detect it. I may not be able to tell you exactly where the problem is, but I know that I should know that there is a problem. So what can we do that? So where do I put this stuff? It could be an aggregation tap or switch span session inside the customer premises. Some of you may have gone to the session in the Zoom 2 session just before this. And they were talking about putting in these giant instrumentation environments, and it could be there. So we're going to have taps and spans feeding into it, in our sites. I don't quite have that same thing. I don't quite have that same visibility inside AWS, for instance, but actually there is a mirror. So there's this, for AWS, there's a VPC traffic mirroring. It's a capability that AWS has just started providing within the last year. And Azure and GCP have similar capabilities where basically it's essentially a software-based tap span, how it's physically working. They keep that information from us, but the idea is that we can feed it into this DPI probe. And I'm showing it here along this path, but it's even possible to insert that further in. So not just for the edge of the network, but deep inside of there, if that's what you need. So by getting this visibility there, and it's packet level visibility, we can see when there are network issues, even if we're not, as I said, even if we're not monitoring the network devices themselves, we can see their behavior. And the biggest piece of that is, I'm going to call them flag packets, because we're at SharkFest, and that's what Wireshark does. If you've seen the TCP analysis.flag, that's what we're looking for. Is there a missing segment? Is there a retransmission? Is there a duplicate hack? Are there connection failures? Retransmitted SYNs, resets, what have you? All those things that get flagged by Wireshark, those are all the same thing that these DPI probes can be looking for. And that means that we should be able to tell in real time or near real time when we have issues in our network. Again, even if we're not, if I can't tell what device it is that's failing, is it a switch? Is it a connection? Is it a route that's failing? No, I don't really know. I do care, but just the fact that it's failing is enough to help me move on and get some more data. So what does this mean to us? This means we can see when we have packet loss, when we have, and we put in there in the title to this slide, these micro outages, and these are some of the ones that are pretty painful to us. Availability zone failures. interface losses. If the load balancers go down, okay, I'm in East Coast right now. I do want to tell you, it's what, 7 o'clock now. I actually got I told you we do operational support in my team. I happen to be on call this week. I got a call at 3 o'clock this morning. There was an application that went down. It turns out it was a load balancer failure, and we were able to see that by looking at the network. And so that all this packet level stuff that we're so used to with Wireshark, we're applying it to the cloud environment. So lots of things that we can do with this, even if it's not the same visibility that we have, for the networks that we directly control. All right, so you're probably wondering, when am I going to see the packets? Well, here we go. So I pulled some examples. I've got 3 examples that I provided, and I'm gonna walk through them for you. Hopefully you saw in the chat that we have somewhere in there in the chat. I believe we've got a download. I put these 3 packets, and I also put a little bit of the same thing in the README file, so you can take a look at that. Take a look at these trace files, and I'm going to give you a minute or 2 to look at them. Not too much time, because I want to look at them myself as well. But take a look at each of those files, or probably just look at the first one. I have some suggestions. I think put a display filter in for the TCP analysis flags equals 1. I mean, they're true. So we have a TCP analysis flag on there. Take a look at the IO graphs. I'm not seeing very many people doing that, but it helps me tremendously, and you'll see why when you take a look at least 2 of these. It's going to be really, really helpful. And inside the IO graph, don't just look at packets per second. I suggest that you also look at perhaps the flags and the retransmissions. That'll give you some idea. And in the display filter, you might also, in addition to just doing overall flags, you might look at the retransmission counts as well. And then let's take a look at some other stuff. All right, so I'm going to go over and switch to my my first trace file. That's SF SharkFest 20 trace 1. I probably should have put my name or something better on it, because you're going to lose it with all these traces that you're going to be working on these 2 days. So the first thing I'm just going to do is I'm going to look at flags. I built myself a little filter button there. I don't have too many of them. TCP analysis flags. So you don't actually need the equal 1, so that's fine. So that goes and grabs these things. I'm just showing the real time, and down here in the status bar we get some interesting information. Now I'm going to give you some hints. I believe on all 3 of these I only fed you with 1 TCP connection. It makes it a little bit easier. So we're not, if you were to go to look at the statistics and the conversations, it's just 1 IP pair and 1 TCP pair. Obviously, when I'm looking at this stuff, it's a lot more than that. But this helps us to understand, because we're going to look at anything like sequence numbers and so forth. This can really help there. So the next thing I was thinking that you might want to do, because I do it, is I bring up a graph. And what we have is we have some very bursty traffic, but we see that there is a period where essentially we have no data. And it may look like, let's take this one out for a second. So this is just our throughput. It may look like we have data, but if you actually overlay it with the retransmissions piece, so that's just a display filter saying tcp.analysis.retransmissions. But if you actually overlay it, all the packets that we're seeing during that period are actually they're all retransmissions. So something was going on there. And now let's go back and look and find that point in time. And let's go back. So that was about so I tend to zoom in to find this. The zoom in only gives me 1 second resolution, but that's good enough. So somewhere around 10, 12, 31, 32 to 39 is where we need to be. Because I have this up right here, I'm just going to choose this 10, 12, and I'm going to disable that filter. And I essentially would be right at hopefully the beginning of that interval. We're pretty close. And we got these wonderful little pieces here. I don't even know what they're called over on the right side. I'm just going to click on that to get to sort of the high point. But we see 10, 12, 31. So this is, let me just go back. So 10, 12, 31. So that's in the middle of that outage. And if we just go look through, and 10, 12, 40. So right here, we have a big jump in time where nothing happens. This is what we're worried about. Now, before I get there, so we'll cut to the punchline later. Sometimes we get some things. I have a previous segment not captured and a TCP out of order. So this is a packets getting out of order, but it is packets getting out of order in the monitoring environment, not in the real world. Because if it was in the real world and it had packet out of order, I would have seen a duplicate ACK. Let's see some of these other things. Again, we have packet missing, and then it's received out of order. That's the same thing. Sometimes though, we get some previous segment not captured that we don't have an out of order following that, and that's sometimes you get packet drops inside your monitoring environment. It happens. But in this case, and that's right here, this is, again, they get out of order, and this is in the monitoring, not in the real world, because of lack of duplicate ACKs. And this one later on, we do see duplicate ACKs. So when I take a look at this, I'm looking through there. So I've got two sets of IP addresses. If you're wondering about those, I've got 10.0.1.1 and 10.0.2.1. Well, I do want to tell you those are not the real IP addresses. This has all been anonymized by making use of Trace Wrangler. So thanks to Jasper for that. These are not the real IP addresses. These are not the real port numbers. There's no data inside of here. It's all been truncated through use of Trace Wrangler, which means that I can pass these off to you. So I'm just going to say that the 10.0.1.1 is some sort of remote system that's not in AWS, and the 10.0.2 is always that's the stuff that's in AWS. And what we see is that we stop hearing from AWS at this time, 10/21/31. Let me actually, one of the things I tried to do is I'm going to set a time reference, and then instead of doing this with local time, so let's change our time display to from beginning of capture, which actually becomes from beginning of reference as well. So we're 60 seconds into it there, and then I reset that reference. So what we see is that we last heard from our AWS server at this time right here, and we next heard from it 9.4 seconds later. And in the meantime, this remote system has been sending data to it and not getting any ACKs back. So he then goes and sends some more and doesn't get any ACKs back. And then finally, 9.4 seconds into this, we get an ACK back. So this is one of these things we're terming these micro outages, where we're seeing AWS or some of our instances basically stop responding, and it's because there's some disconnectivity inside the AWS environment. This one lasted about 9.4 seconds. If we had other samples, we might have found that it might have started responding sooner. That was just, this one got through, so there was nothing that was sent to it between 5.3 and 9. So it might have been a little bit less than that. It might have been as short as maybe 5.4 seconds. but this is a good indication for this connection. The outage lasted 9.4 seconds. And actually, when we take a look at this ACK, so this is an ACK for 66357. It's actually ACKing this. Well, it might be this one, but it's almost certainly ACKing this last one that comes out here. It takes about 41 milliseconds there, which is still quite a long time, because normally we see those ACKs coming back much quicker. Now the impact lasts a little bit longer, but essentially within 4 milliseconds or so, we've retransmitted all of that. We've retransmitted that data, and we've caught up. But if you have applications that have sub-second response time requirements, and you have an outage lasting for essentially 10 seconds, you can imagine whatever transactions arrive during that 10-second interval would have timed out. So this still can be quite painful, even if we do retransmit that, because we're a transactional environment at Capital One. Yeah, we have lots of batch flows as well, but when we have transactional stuff, this becomes very important. Okay, let's see. I'm going to take a look at questions. Would you run? So I got a question. Would you run reorder cap on this? You could. That could fix these small things, but the thing is, I'm not always sure. I don't necessarily want to do that, because a lot of times we do have out of order packets that we care about that are causing retransmissions. So trying to fix them if they are real problems. So it's not something I do as a matter of course. I have to take a look at them and determine whether I can ignore them or not. But in this case, I'm looking at this. This was the outage, and in fact, let's take one step back. Why did I even look at this? And it turns out that these few retransmissions, if I took a look at these retransmissions, 25 retransmissions, and in fact, there was a smaller number just during this thing, probably only about 10 or so, was enough so that I saw there was a threshold that was violated in my DPI probe and generated an alert. That alert correlated with something with an issue that the application was seeing. Well, why do we care? It's all fixed. By the time I took a look at this, it was all better. But once these things start happening, sometimes they repeat, because if there's an issue in the hardware, now AWS, they might not care. A 10-second outage to them, they just, for whatever reason, that might not be the most critical thing. But for us, if we see some of these things, like maybe once an hour we see this happening, that might be an indicator that we need to get out of that environment and have AWS look at it in more detail. So there is something that we can do about it. Okay, so that's trace one, and if we need to revisit that, we can do that in the question and answer session. I'm now going to go and look at trace two. I think I had already looked at that. Yeah. Okay, so here's trace two. I'm just going to follow that same thing. Let's just look at the flags. Well, okay, 12% flags. How many of those are shown as retransmissions? And I always look at retransmissions. That's usually the biggest indicator of problems in my environment. So I'm always going to retransmissions. And unfortunately, we sometimes get some false positives from our DPI probes. What does it mean to be a retransmission? If they don't deduplicate properly, that can cause some false retransmissions. Sometimes it might flag when just packets are missing because of when they're missing or reordered, thinking that they're retransmissions. So we need to check this thing. But in this case, it's saying out of my total of 2,800 packets, 5.8% of them are being marked as retransmissions. That's a lot. Let's take a look at the IO graph. This one's going to look quite different. All right, here we have it. Actually, sometimes it throws. Okay, didn't do it that time. Okay, so we got the same two graphs. So if we ignore the retransmissions, we can. Somehow I clicked that twice. If we ignore the retransmissions, well, already we can see this is very bursty, and we can sort of imagine what's happening here. you know, rather than having you guess, because it's not quite as interactive as having you sit in front of me in a giant coliseum, I'm going to tell you what is likely happening here, which is we have some processing going on. It grabs a bunch of data and then pushes it to a server. So basically, there's a batch process. It harvests some transactional data and sends it off streaming to be processed. So 80 packets, you know, per second, but it's all done in a short interval. So we have these bursts of data, and when we look at the retransmission, so I'm going to turn off the throughput and look at the retransmissions. We actually had no retransmissions, and it was a very clean environment. We had no retransmissions, and then all of a sudden we started seeing retransmissions. Actually, it got worse over time. I only looked at the first, you know, the first few minutes of this particular issue, and this was a very high throughput file transfer. This connection was a small piece of actually many, you know, hundreds or thousands, I'm not sure, of other connections that were all going to the same place. And what was happening is a little bit strange. So let's take a look at this in a little bit more detail. So, you know, 5.8%. If we were all, by the way, if we're only looking at the, you know, if we ignore the first 30% of this, actual retransmission rate, once we get into this problem, was actually closer to about 8 or 9% retransmissions. All right, let's just go. I'm just going to jump into the middle of this. Again, we're looking at one connection. I'm going to turn off my filters. Now, if I wasn't already looking at one connection, what I would have instead done is go to conversation filter TCP. This is going to be equivalent because there is only one connection there, and that's so that I'm only looking at that one connection. By the way, I know some of you might prefer to do it a little bit differently and to follow a TCP stream. In our case, you know, we have that one of the side effects of that is that it shows you all of the data bytes. Well, I don't have any data bytes. These are all sliced packets. So this is actually more efficient, and so I would suggest doing this. It also allows you to see exactly what that filter is, rather than looking at that connection ID, which is, these are coming from the actual packets, and the connection index numbers, those are Wireshark. They're just created by Wireshark. So this is reflecting what you see in your packet, so it'll be repeatable even if you have a different trace that's smaller that's looking at those same connections. All right, so let's take a look at this one again. We have a retransmission, but we see this is not the behavior that we saw before. This is not an outage. We could look at this in further detail. So one of the things we can do, let's look at 100 millisecond. Let's get it into more detail and then zoom in on that. Yeah, so we're not seeing outage. We get retransmissions when we have these spikes. If I go too much closer into it, it doesn't really help. I can do it, and then we can zoom into there a little bit more. So we even inside those 1 second bursts, where it's bursty even inside of there. But let's take a look at this in a little bit of detail. So this packet, this packet right here, this first retransmission. So what is it a retransmission? It's actually, you notice the little dot right there. So it's a retransmission of this packet, this packet here. So, you know, when we look at this, well, why was that retransmitted? Well, in this case, it was only 21 milliseconds. You know, why did it feel it needed to retransmit? Well, certainly it didn't see an ACK. So there's something going on there. And then if we go and we look at the next one, so what is this This is saying it's a retransmission. But if we take a look at the sequence numbers, yeah, 229608071. That's a retransmission of this frame right here. Perhaps actually, let me just make sure. Yeah, this one is a retransmission of this. This is a retransmission of this. Again, we didn't get any acts. When this thing was working, we were seeing these acts come back. Here's acts, and then here's an application level message. Here we're seeing a retransmission of first this packet and then this packet. I'm not sure why it retransmitted this one rather than starting with the first packet. Not really clear, but that's the order in which we saw the retransmission. And this one took 200, it was 200 milliseconds before that was retransmitted. We can do that same thing with setting a time reference here. And we can see, yeah, so that was 200, it was 233 milliseconds from that packet from the first instance to the second one. This time we do get an acknowledgement, and this is actually the acknowledgement for this frame here. So we got that one. Now notice it didn't acknowledge this one because this is not, we're missing a bunch of intermediate frames as well. So now it goes through and retransmits to come up, catch up to all of this stuff, but there's still a bunch more retransmissions that are happening. It finally retransmits this one yet again, this 5092, it retransmit yet again. And does it get an ACK back for it? Yes, it finally gets an ACK back for it. So we had to retransmit multiple times before we finally got everything back, all the ACKs back that we needed to know that we got this through. But essentially what we're seeing is we have some packets being lost. It was just this group of 1, 2, 3, 4, 5, 6 packets. All the other stuff was working fine up until then, or so it seemed. And then we go and we have another group, and we have another group. And this is a very different behavior than what we were just looking at in the first trace. So this is random packet loss, groups of packets being dropped randomly somewhere inside of AWS. And how do we know that this is AWS? It's because we're right on the edge. So we're seeing, we saw the packets going into AWS. The 1002 is AWS. We saw the packets going into AWS. So we know that it's to the, in my thought, it's to the left side and it's not to the right side, because we saw it go in, but we didn't see X coming out. So we know that when we look at our diagram of the network, so let me go up a few. If we're monitoring right here, we know that the packet loss is on the left side of that. So, and that's true whether the probe is there or there. It's still to the left side. So depending upon where your probe is, that that tells you how many things you need to look at to understand where the problem lies. But when you're sitting somewhere in the middle, you can always determine left side, right side packet loss. So we've got this left side, towards the AWS environment packet loss, and we're looking at this. So this was a fairly hard thing to look at, except for one thing. We saw this high throughput, high traffic volumes start to happen, and as the traffic volumes increased, that's when we started to see the packet loss. As soon as the volumes dropped back down, the packet loss went away. Volumes go up, the packet loss happened. So it looks like there's a bottleneck somewhere in the environment. So I'm going to switch back to our slide thing, and yeah, so trace 2. So that looks like congestion. There's some bottleneck, and it's when you tie those things together. Well, so AWS, when they first came out, all their interfaces had this thing called a VIF, virtual interface, and they basically supported about 1 gigabit per second. And you could never nail down AWS on exactly what they did. They then came out with what they called Nitro, This was about 3 or 4 years ago that they started offering this as an option. So even when you scale up to your biggest servers, you would still, out of the box, you'd only get the VIF interface, which is this virtualized network interface that worked very nicely with their SD-WAN. Well, if you needed more, on the larger ones, you had the option of a physical interface that would be dedicated to your instance. Yes, there's some virtualizations on the way to get there, but you basically could get the entire 10 gig of an Intel 82599. And then later on, they introduced this ENA, this enhanced network architecture, and that would allow you up to 25 gigabits per second. And I say up to because you needed to basically dedicate that box to it. I mean, you had many CPUs and so forth. You might not be able to get that. But when you're trying to get high throughputs, you need to be making use of what they call the enhanced networking features. And that's what this case was. So we were using the standard, actually, I'm sorry, in this, I think we were using the Intel 82599 environment, and we needed to switch over to the ENA. So we needed to go one bump up in terms of the networking options. One problem with this that I'm going to really, I think it's a problem, is that the packets were being dropped, and we could go to AWS and they could see the packets being dropped, but our monitoring never showed. So there is no packet drop on the interface. It's not a metric that we have visibility out of the box from AWS. So instead, it's only when we see it happening in a real world in a trace, or somehow on the application we need to detect that. Applications don't really detect retransmissions. They detect slowness. If you're not getting the throughput that you expect, then you might need to looking at packet traces to see this. So that's exactly what we had to do. We had to go and get packet traces. We then worked with AWS, and they said, "Oh yes, we can confirm that we were dropping stuff in either in the VIF or in the 82599 environment, and you needed to move to a bigger size." But the amount of convolutions you had to go through to get the right people at AWS, because it's not an out of the box analysis that they do. They certainly don't provide it to the customers. So you need to have something like a packet trace analysis to be able to show that you're dropping packets as you get to higher throughputs. Do the calculations yourself and see if you're there. And if you just look at your throughputs and you see that you're getting close to 10 gigabits per second and your performance is leveling off, that might be your issue. Okay, so now I'm going to switch over to trace number 3. Let's see what we got there. Okay, I'm going to go through the same process. I'm going to look for the flags. Total flags, only 19 flagged packets out of 4,000 packets. How about retransmissions? 4. If I was looking at traffic going over the internet or traffic going over my Wi-Fi segment, I had 4 packet drops out of 4,000, with retransmissions. I'd say not a problem. Move along. There's nothing to see here. There's nothing to see here. I mean, those kinds of packet loss you see all the time, especially when you're going through public environments. But remember, I told you I'd like to go and look at the IO graph and look at that. So even with only 4 dropped packets, at least measured by my interface, there was something else. Yes, it is spiky. It's a bursty environment, but we never really. I mean, well, down there, I guess we went down to close to 0 packets. Maybe 5 or so packets per second. But now we go and we have a sustained 0 packets for 20-some seconds. How could this be? So this actually is a case where even this small amount of flagged packets, these duplicate acts, And the retransmissions, even that small amount, our DPI probe did point it out, but this is one we had to drill into really, really tightly because it was the application monitoring that said we had a big problem. So how can this be? How can retransmission, if we got this big, giant ass outage, how come we don't see more retransmissions? So let's just take a look at that. So what is the flow? Who is the client? Who is the server? What is the traffic flow? So if I'm looking at this, I'm just looking for a break here. So I'm seeing, okay, I've got one direction, then another direction. So I see the large packets, 1348, 1348, 1348, 1348, with an ACK 1348, 1348, 1348, 1348, ACK 1348, 1348, and a little bit. Oh wait, and some more. So this is mostly data coming from the cloud and being acknowledged. And every once in a while, you'll see, I'm not even sure if I'll be able to just sort of glance at it and see. But for the most part, this is data just coming, this is one-way data coming from inside AWS and going out. So by sitting here with my little monitor sitting on the edge, when I'm looking at this, if stuff stops coming, I'm not going to know that there's a problem because I'm not going to see any retransmissions. Because yes, there may be retransmissions. He's not getting the ACKs when this incident happens. Now let's find that particular incident. So it's true that there's not ACKs. But let's just look at the last time we see data from that one. I'm just eyeballing that, and I'm going to set my time reference. So this is the last data segment I see before there's a 21.9 second period where we hear nothing from there. And actually the last packet that we saw did trigger duplicate ACKs. That wasn't actually the last packet. So there were some packets that were lost right as it was going down. It was a little bit problematic. And then we start to see the data coming from it. But now we're seeing a whole bunch of duplicate ACKs because there was one of those packets right at the very beginning which was missing. So it's the duplicate ACKs that are the biggest piece of the puzzle right here. And not seeing any traffic for 20 seconds. I'm going to tell you something. Our DPI probes, and most of them, they aren't looking at 1 second granularity. Usually, you're talking about 1 minute or higher granularity. So yes, we see a throughput drop when you're looking at 1 minute granularity, and we did see that, and we see a spike in retransmissions, but the retransmissions are very low. But you needed to look at that duplicate ACK piece to see more. So you need your DPI probe to be smart enough to look for duplicate ACKs as well and do something with them, so that will also generate something so that you'll know. So when we go through this thing, yeah, we had some retransmissions, and look at this. Even while we were doing those retransmissions, there was a jump here, 5 seconds. Notice I've got 2 time columns in here. One which was, when I started out, this was showing clock time, wall time. Another, and I changed it. That I can easily change by looking at the format from time of day, for instance, to looking at it by seconds since beginning of capture. And then I have another one. Now what is this? What is this field looking at? So that one, sorry, shouldn't be clicking on that. That one is looking at the time since the previous packet. That's our TCP time delta right there. So with our TCP time delta, we also see that there was still, even before it finished before it got the retransmission done, there was another 5 second gap. It was actually, till the time we caught up, that was a 27.2 second outage before we finally got the missing before we had a retransmission there, so we had all of this, but we're finally started moving along 27.28 seconds here. So this is a pretty significant outage, even though the metrics, those flag things I was talking about, the retransmissions, the duplicate acts, weren't very large in magnitude. Total of, I don't remember very long, a total of 20. And some of those were even before the period that we're talking about or after. So we're only talking about 16 or so flag packets that were an indicator of essentially a 27-second network interruption. And if let's look at that on our graph. So what is going on? I think I'm probably, sometimes this doesn't work out. So 2204, 2204. What's going on there? That's not what it looked like when I first brought this up. Okay. I'm going to plead ignorance and just open that over again. Okay, there and there. So when so I'm not sure what was happening with that, why that IO graph was not working. But when we look at this and zoom into it for more detail, so this is that initial 20-second, 22-second outage, and then it was another 7 seconds there to bring it to 27 seconds before it actually. So there was a little burp while it got sort of caught up, but then it didn't finally fix itself until 22 and 30 point something seconds. So this was really quite a long network outage. The instance obviously didn't go down. It was still trying to talk there. It was actually trying to retransmit, but the packets it was sending were not getting to their destination. In this case, getting routed outside of AWS. All right, I'm going to stop for a second and take a look at remove the time reference. Maybe, yeah, I probably should have tried that. That may have given it, that may have broken it. That it was wrapping. Maybe it was wrapping the stuff with the two overlapping time references. It started back from 0. Is there any way to tell if the outage was from a noisy neighbor VM? And there's not an easy way. So that this would be probably for that first one or this one. Is there something that caused it to go down? And so maybe, but I don't care, because if we're not able to talk to our EC2 instances because of something else, then our environment is not protected. So I don't always have the answers, but let me go on in the presentation and say, so once we see these issues, we get packet traces so we can confirm it. So just the fact that we see a blip on our DPI probe, that's not enough. We need to take our due diligence, 2-3 steps further and get packet traces that show, because if it's talking to, say, a client who's in I don't know, New York City, maybe the problem's in New York City. So we need to look at the trace to figure out, is it on a left side or right side issue? And maybe we're going to take some new traces that are even closer. So get those packet traces so that we can verify that it's inside the cloud. But then what do you do? Because this is why we're here in the first place, which is we want to have visibility to the network inside the cloud. So what do we have to do? We have to actually open a ticket with the cloud provider, AWS, GCP, Azure, what have you. And we need to give them the details. And I'll tell you, don't just sit there and wait for them to call you back and then try and talk them through it. Put as much details as you can. If you have packet traces, put them into the ticket, because if not, you're not going to get the right level of person who's going to be able to deal with this. So give them the details that needed. And by the way, they don't know, they're not experts in collecting packets. You're the expert in collecting packets. So you need to tell them, where did you get this? If you did the capture inside their environment, was it a VPC port mirror? Was it collected on an instance? Was it collected on an interface directly connected to the direct connect? Yes. So was it on the direct connect interface? Where did you get this data? So put that in there as well. And don't assume that they know how to read a packet trace. So put little arrows in there, like this thing. Oh, this is the last time. Well, let's go back to this one. Here's the last time I heard from your device, and we didn't hear from it again until 9.4 seconds later. Put that information in there, because when you have those details, share it with them. If the first tier guy doesn't know how to interpret that, he's going to bring on the right level guy, or hopefully you'll get them quickly. So what do we hear back? So I have to say, we usually don't hear something back immediately. That's just the reality. Even for some of our, especially if it's something, it was a transient thing, they're going to look into it and maybe get back to you. If you've lost a high priority application and it's happened multiple times, you need to get an answer quicker. You may not be able to wait for that. One of them is, they took a device out of service, and that was the routing time to reconverge after removing it due to taking the device out of service. And they didn't think it would impact anything. We saw, there was a failure to a particular availability zone that affected direct connect links. This actually, after we see these things, then those kinds, might even show up in alerts that they send out to their customers. The one about our interface was too small. You need to upgrade the network interface on your particular instance. But what you don't want is that other one on the bottom. We were unable to determine the cause of the issues that you were facing. So that's disappointing, and you want to avoid that as much as possible. And from dealing with these types of issues for a while, it's important to be insistent. Say that you saw this problem, you're able to prove that it was inside the AWS environment. And once you build up those things and you build up, and they start to trust that the data that you're getting is true and accurate and reflects outages that are affecting your applications, and it has an impact on those, then then the prioritization of this starts to go up, and they assign this to people who actually can see into that. A lot of times you're working with the people who are assigned to the role of interfacing with the customers, and not with the people who are working on the engineering and the operation of especially the network environment. I got some more questions. In a real-time environment, are the packets captured so they can be looked at if any incident happens? Yes, after a fashion. So not always. So that's a goal, but it's not you don't spend so much money to set up these monitoring and visibility environments to capture every packet for every potential incident. You want to identify what are your critical components and make sure that you have the resources that you need for them. Any way to show packet comments as a column? I don't know. That talk to the Wireshark guys. I'm just a user like you. If you capture in the AWS environment, do you bring traces out to run Wireshark? Oh, yes, absolutely. Yep. Yeah. So for production environments, we're not running Wireshark inside our production environments. We're using other tools to capture data in there and offloading it and doing doing it there. So yeah. So yeah, I do the analysis. A lot of times I'll do it on my laptop. And we also have some analysis environments inside our network. Obviously, if the data was collected with one of those DPI probes, then we can either do the analysis on the DPI probe or bring also analyze it on another machine. So, but you're gonna need to use something like Wireshark. You need, in most cases, you're gonna need to have this packet by packet view, not just the summarized metadata that's coming that we had, that it detected during that 1 minute for that conversation. It detected, 22 retransmissions. You're going to need to see what they are with the packet data. Show me the packets. What did I learn here at SharkFest? The packets never lie, so you need the packets really. Okay, do we have any more question? I probably should be marking these things. Answer. Right, okay. Through the time. Thank you. Okay. Okay, something like that. Okay, let's get back to the presentation. I've been going on here for, have I been doing this for an hour? I guess I have. Okay. Oh, here's another example. This is a recent one, actually, October 9th, 2020. We are investigating network connectivity issues for a small subset of newly launched EC2 instances within a single availability zone, US East 1, AZ2, and US East 1 region. We have identified root cause and are working towards resolution. This is the type of thing that you might see, and that might correlate with your issues. By the way, don't always trust when they say a small subset of newly launched EC2 instances. I don't know what newly launched means to them, but if you're seeing anything that is affecting some of these servers, sometimes they may put some boxes around their description of the problem that are overly constraining and don't really reflect the reality. So if you start to see issues, starting at perhaps before 148, because that's only when they did the first announcement, and all the way until they tell you that it's done. So take a look at the AWS Service Health Dashboard. And as I said, there are very similar dashboards, and by there's RSS feeds and some other ways of getting this to be able to get alerts directly on your platforms. So take a look at those things because they may correlate with some of the issues that you're facing. What you don't want to have happen, which has happened to us, is you report it to them and then it shows up here. Ideally, AWS should be identifying as soon as it happens because they have the network visibility inside their environment. It's not always the case. So that's why you need to do the investigation. When you have something, please report it to them. That may help other users as well because now it might show up on their dashboard if they didn't catch it before. All right, so we got cloud. What about the traffic that doesn't feed into our DPI? I mean, we already talked about this a little bit, so that you can perhaps you can do some capture on the instances, but there's some other things. So yeah, third on there is capture on the instances. Well, okay, the first one is actually redundant. Traffic, set up a traffic mirror to a collector, or maybe to your DPI. But then if it was DPI, then you're not, this isn't the answer to that question because it was in your DPI. But traffic mirror doesn't always have to go to a DPI. Maybe you can do that to a packet collector that's going to allow you to do analysis after the fact for troubleshooting, for forensics, rather than for real-time monitoring like a DPI probe. Flow logs is another good source of data. So all three of the major IaaS, PaaS vendors provide flow logs, so that you can take a look at traffic, very much like NetFlow. I'll talk about that in a second. capture on the instances, TCP dump, whatever Wireshark used the dump cap, what have you. And there's a lot of other network data source that go into logs, I would say. So your firewalls, proxies, internet gateways, NAT gateways, even your content delivery networks, a lot of log files that we're going to have some other data that's going to provide you with additional information to help you understand what's going on and see what you have from provider specific alerts that may say your direct connect link is down or some other thing. Though, looking at an AWS environment, looking at the CloudWatch metrics that are provided for those different platforms. And I do want to talk about one of these in great detail, which is the VPC flow logs. Similar to NetFlow, you do have this 5-tuple of IP port and protocol, but it also has an account. So you actually can get that IP port protocol be seen in multiple accounts, especially if you have 2 accounts talking to each other. So you might see it twice. And it also has some security information in there, which is a little strange, but okay, we'll take it. So if something was blocked because of a security group or a NACL, you would see it show up as reject. That can help you a lot right there, because there is some security inside of there that's different from those firewalls and so forth that we were talking about. And then you have the packets and the bytes. Now, it used to be that they waited till the connection was closed and then they would throw that out, and then they started throwing out some intermediate logs. Now you can actually turn it on so you get them per minute. You can set the granularity so you get records every minute. So you have near real-time visibility with these things. So it's a lot of data. They just introduced, I say just, but within the last year they added TCP flag. So I had 10 packets. There was a SYN in there, there was a FIN, and there was a reset. That's important information. There was push bit. If you didn't see a push bit, then you probably didn't even send any data. What if you only saw SYNs but no ACKs? That probably means that you had a connection that failed. They're including the subnet, VPCs. They're also including NATed IPs. Now, this is pretty important because as packets pass through the environment, they may have one set of IPs to get NATed to another set. So inside each account, you have the ability to have additional NATed IPs added into this VPC flow logs if you're using the latest version of VPC flow logs. VPC flow logs, hard to deal with. That huge volumes. Yes, so you need a log management system. Yes, they are captured and stored. You can look at them manually on each individual instance, but you really need to be processing them through a log management system like Elk. That's your Elasticsearch, Log Stash, Kibana, Splunk Datadog, or a SIM if you're on the cyber side. That right out of the box, you can very easily get some throughput monitoring. It does have security pieces in it because of the NACLs and security group rejects. And I suggest that if you're going to be taking the trouble of processing this, that you associate it with your applications and location information so that you can get extra value out of that. And I also went one step beyond that, and I was able to infer connection failures. So even before we had the TCP flags, we could do that. To set up a TLS session, you have the 3-way handshake, SYN, SYNAC, and ACK. Then you have a client hello, server hello, and 2 more back and forth. You need to have 5 turns at a minimum to be able to open up a connection. And then you need to send a request, and then you're probably going to need to close it if it's a short-lived one. But maybe we can. So if you have a new session, if it has less than 6 packets, you probably didn't get all the way through the setup. So here's an example of using that. So while I would love to have packet for looking at everything, sometimes we don't have that. And I need to fall back on looking at the VPC flow logs. So here's a case where we looked at connections to, yes.
We are out of time. It's 5 p.m.
Oh, we're out of time. I'm going to take 2 more seconds and
okay, Afterwards, you guys can continue the discussion over to Discord in the Zoom one chat.
Yeah. Okay,
perfect.
so VPC flows, we can get connection failures from that. You can also capture on your instances, and you need some mature processes to be able to do this. I talked a whole bunch about this, and there's a lot of commercial tools, open source tools, and what you see today is not going to be the same as what you saw a year ago and what you're going to see a year from now. To which I say thanks. And now we can, if we had any more questions and answers, because I know I went through them, thank you very much. Hope you enjoyed it, and I will go and look for more questions. So for the questions, okay, are your DPI probes in the cloud or are they on premise? Yeah, yes they are. Sorry, we're really not talking about how we do this. We don't want to get into a lot of technical details here. But suffice it to say that it's not just one set of DPI. There's a lot of possible DPI probes, and there's a lot of different ways of doing it. And we have what we think is a very good solution, but it's also an evolving solution. Do we use CloudShark at all? No, we. So I think the answer is no. But there's a whole bunch of caveats to throw around there. Again, I don't think it's we don't want to go into a whole bunch of details about how we're doing things at Capital One, but we're very happy with our ability to support our high value applications, and I'm in the network side. There's also people on the cyber side, and also to protect that entire environment by having the visibility that we need to this environment. Okay. Do we have any other questions?
I think we need to close the session because we need to start the next one.
Yep, sounds good. All right, thank you very much, all.
Thank you.
I can go to Zoom one chat.
Perfect.
On Discord. Bye.
Thank you.